Hello, and welcome to the Deep Sleep Discoveries channel. I'm glad you're here. Tonight, there's nowhere you need to go and nothing you need to solve. This is a quiet place to let your thoughts loosen their grip while we drift gently among islands of stars, vast collections of light scattered across an ocean of darkness, each one a galaxy, a world unto itself, turning slowly through the void. There are so many of them, more than we could count in a dozen lifetimes, and each one holds stories written in starlight and gravity, in gas and dust and the pull of invisible things we're only beginning to understand. Let yourself settle into the quiet darkness of space. Feel the gentle weight of the night around you. We're going to explore these celestial islands together, 100 facts at a time, each one a small window into the grand architecture of the cosmos. There's no rush, no urgency, just the slow unfolding of galactic wonder, the kind that invites rest rather than restlessness. So close your eyes if you'd like. Breathe slowly, and let's begin our journey through the galaxies. A galaxy is a vast collection of stars, gas, dust, and dark matter, all bound together by gravity. Imagine gravity as an invisible thread weaving through space, pulling everything toward everything else. In a galaxy, billions of stars circle a common center, held in their orbits by this fundamental force. Between the stars float clouds of hydrogen and helium, the raw materials for new suns. Dust grains, smaller than particles of smoke, drift in the darkness, sometimes catching starlight and glowing softly. And threaded through it all, invisible but ever present, is dark matter, a mysterious substance we cannot see or touch, but which provides most of the gravitational scaffolding that holds the galaxy together. These components don't exist in isolation. They interact, influence each other, create feedback loops of formation and destruction. Stars are born from collapsing gas clouds. They live their lives, some peacefully, some explosively. When massive stars die, they return enriched material to the interstellar medium, seeding future generations with heavier elements. This cycle has repeated for billions of years, and it continues still in our galaxy and in countless others scattered through the universe. Each galaxy is a self-contained ecosystem of cosmic evolution, and among all these galaxies, one holds particular significance for us. Our galaxy, the Milky Way, contains between 100 and 400 billion stars. The uncertainty in that number reflects just how difficult it is to count stars across such immense distances through clouds of obscuring dust in a galaxy we're embedded within. We can't step outside to see the full picture. We're like someone trying to map an entire forest while standing among the trees. Yet through careful observation and mathematical modelling, astronomers have estimated that our galactic home is populated by at least 100 billion suns, and possibly as many as 400 billion. Each one is a nuclear furnace, fusing hydrogen into helium, releasing energy that travels across light years to illuminate the cosmic dark. Some of these stars are larger than our sun, burning brilliant and blue, destined for short, spectacular lives. Others are smaller, cooler, redder, stars that will burn steadily for trillions of years, long after our sun has died. And scattered among all these stars are planets, moons, asteroid belts, comets, entire solar systems we're only beginning to discover. The sheer number staggers the imagination. 100 billion stars, each one a potential sun for worlds we'll never visit, for stories we'll never know. And yet, for all this abundance, the Milky Way is just one galaxy among multitudes, and galaxies themselves come in different forms. Galaxies come in different shapes, spiral, elliptical, and irregular. This simple classification helps us organize the bewildering variety we see when we point our telescopes toward the depths of space. Spiral galaxies are perhaps the most visually striking. They have graceful arms that curve outward from a central bulge, like cosmic pinwheels frozen in a very slow rotation. These arms are rich with gas and dust, sites of active star formation, glowing with the blue light of young, hot stars. Elliptical galaxies are quite different. They appear as smooth, rounded or oval collections of stars with no spiral structure, no distinct arms. They tend to be redder, populated by older stars with little ongoing star formation. They range from nearly spherical to highly elongated shapes. Then there are the irregular galaxies, which defy easy categorization. They have no symmetrical structure, no orderly rotation pattern. Often they're small, sometimes chaotic. Their shapes distorted by gravitational interactions with neighboring galaxies or by intense bursts of star formation that disrupt their structure. These three basic types, spiral, elliptical, irregular, provide a framework for understanding galactic diversity, though many galaxies blend characteristics or sit between categories. And whether spiral, elliptical, or irregular, all galaxies share one curious quality that's easy to overlook. The space between stars within a galaxy is mostly empty. When we look at images of galaxies, we see them as bright, densely packed collections of light. But this is an illusion created by the limitations of photography and the vast distances involved. In reality, the space between stars is almost incomprehensibly empty. If you could somehow stand on a planet orbiting a typical star in the Milky Way, the nearest neighboring star would be several light years away, a distance so vast that light, traveling at 186,000 miles per second, would take years to cross it. That's trillions upon trillions of miles of empty space between you and your nearest stellar neighbor. The galaxy is far more void than substance, more darkness than light. Even the gas and dust that float between stars are so diffuse that, by Earth standards, they would qualify as a near-perfect vacuum. You could travel for years through interstellar space without encountering anything more substantial than a few hydrogen atoms per cubic centimeter. This emptiness is essential to the galaxy's structure. If stars were much closer together, their gravitational interactions would be chaotic, flinging planets from their orbits, disrupting the gentle equilibrium that allows solar systems to exist in stable configurations. The vast emptiness between stars is not a flaw in the cosmic design, but a necessary feature, and this emptiness extends across distances that define the galaxy's true scale. Galaxies can span from a few thousand to hundreds of thousands of light years across. A light year, the distance light travels in 1 year, is almost 6 trillion miles. It's a unit of measurement suited to the cosmos, where conventional units like miles or kilometers become uselessly small. The smallest dwarf galaxies might measure only a few thousand light years across, containing perhaps a few million stars scattered across a volume of space that, while enormous by human standards, is tiny on the galactic scale. Our Milky Way is much larger, its stellar disk stretching across 150 to 200,000 light years. And some galaxies dwarf even this. Giant elliptical galaxies at the centers of massive galaxy clusters can span several 100,000 light years, containing trillions of stars in their vast amorphous structures. To cross such a galaxy, even traveling at the speed of light, would take hundreds of thousands of years. No human journey could encompass such distances. Even our fastest spacecraft would require billions of years to traverse a single galaxy. These scales remind us of our smallness, but also of the grand architecture of the cosmos. Structures so vast they humble our imaginations, yet governed by the same physical laws we observe here on Earth. And the very word we use to describe these structures carries its own poetry. The word galaxy comes from the Greek word Galaxies, meaning milky. The ancient Greeks looked up at the night sky and saw a pale, cloudy band stretching across the darkness. They called it Galaxies Kyklos, the Milky Circle. The Romans translated this as Via Lactea, the Milky Way, and the name has persisted through millennia. But the Greeks didn't know what they were seeing. They couldn't have known that this pale band was actually the combined light of billions of distant stars, or that they were looking at their home galaxy from the inside, seeing its disk edge on as it wrapped around the sky. To them, it was a mystery, something to weave into mythology and wonder. Some cultures saw it as a river, others imagined it as a path for souls traveling to the afterlife. The Cherokee people saw it as a place where a dog had spilled cornmeal while stealing from a pantry, the scattered grains forming the Milky Way. Each culture created stories to explain this pale river of light, and in doing so, they recognized something profound. The night sky invites narrative, demands interpretation. We are storytelling creatures, and even before we understood the science of galaxies, we sensed their significance. That ancient instinct to create meaning from celestial light hasn't left us, even as our understanding has deepened, even as we've learned that those ancient peoples were gazing at something far grander than they imagined. Ancient peoples saw the Milky Way as a river of milk across the sky. In Greek mythology, the Milky Way formed when the goddess Hera's breast milk sprayed across the heavens. In Hindu tradition, it was called Akash Ganga, the Ganges River of the sky. The Aboriginal Australians saw it as a river in the sky where a sky woman lives. Norse mythology described it as the path that souls took to reach Valhalla. These interpretations share a common thread. The Milky Way was seen as something flowing, something connecting different realms, something liminal and sacred. The ancients understood, perhaps intuitively, that this pale band was different from the moon, different from the planets, different from individual stars. It had a permanence, a vastness, a quality that suggested something fundamental about the architecture of the heavens. They didn't know about stellar populations or galactic rotation or dark matter, but they sensed significance. And they were right. That pale band is indeed a river, not of milk or souls, but of stars, billions of them, each one a sun with potentially its own retinue of worlds. It is a structure so vast that light takes thousands of years to cross even a fraction of its width. The ancient mythologies were poetic approximations of a truth that would take telescopes and centuries of observation to fully reveal. And at the heart of nearly every galaxy lies something that would have astounded those ancient stargazers. Most galaxies have a supermassive black hole at their centre. These aren't the stellar mass black holes formed when massive stars collapse, which contain just a few times the Sun's mass. These are monsters, black holes containing millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. At the centre of the Milky Way sits Sagittarius A star, a black hole roughly 4 million times more massive than the Sun. We can't see it directly. Black holes, by definition, don't emit light. But we can observe stars orbiting something invisible, moving at tremendous speeds, their orbits revealing the presence of an enormous concentration of mass in a very small space. We can detect radiation from superheated gas spiraling toward the event horizon. The evidence is overwhelming. There's a supermassive black hole at the galactic center, and it's been there for billions of years. Most large galaxies harbour similar objects. They may have formed early in the galaxy's history, perhaps from the direct collapse of massive gas clouds, or perhaps as smaller black holes that merged and grew over time. They influenced the galaxy around them, their gravity affecting the orbits of nearby stars, their energy output potentially regulating star formation across vast distances. They are both destructive and creative, both endpoints and beginnings, and they sit at the centers of slowly turning galactic disks. Galaxies rotate, though it takes millions of years for a single rotation. This isn't the rapid spin of a planet on its axis, completing a turn in hours or days. Galactic rotation is measured on timescales almost beyond human comprehension. Our solar system, orbiting the center of the Milky Way at about 515,000 miles per hour, takes roughly 230 million years to complete one orbit. This is called a galactic year, and in the entire history of Earth, our planet has completed only about 20 such orbits. When the last galactic year began, dinosaurs had not yet evolved. The supercontinent Pangaea had not yet formed. Life was still mostly confined to the oceans. The galaxy's rotation isn't uniform. Different parts rotate at different speeds, creating a phenomenon called differential rotation. Stars closer to the center orbit faster, while those farther out move more slowly. Yet, surprisingly, the rotation curves of galaxies don't match what we'd expect from the visible matter alone. Stars far from the galactic center move faster than they should, given the gravitational pull of the visible stars and gas. This discrepancy was one of the first compelling pieces of evidence for dark matter. There must be additional mass we can't see, providing extra gravitational pull. But we don't need to travel to distant stars to encounter galaxies beyond our own. The nearest major galaxy to us is Andromeda, 2.5 million light-years away. On a clear autumn night, away from city lights, you can see it with the naked eye. A faint, fuzzy patch in the constellation Andromeda. It doesn't look like much, just a smudge of light barely distinguishable from a distant star. But that smudge is actually a galaxy larger than our own, containing perhaps 1 trillion stars, each one a sun. The light you're seeing left Andromeda 2.5 million years ago, when our human ancestors were just beginning to walk upright on the African savanna. That light has been traveling through the void ever since, crossing the immense gulf between galaxies, finally arriving at your eye in the present moment. Through telescopes, Andromeda reveals its true nature, a beautiful spiral galaxy seen at a slight angle, with graceful arms curving through space, glowing with the light of billions of stars. It's approaching us, drawn by gravity, and billions of years from now, it will collide with the Milky Way in a slow-motion merger that will reshape both galaxies. But for now, it hangs in the sky, our nearest large galactic neighbor, a reminder that the Milky Way is not alone in the cosmos. And Andromeda's spiral shape is just one of several forms that galaxies can take. Spiral galaxies have elegant arms that curve outward from their centers. These arms aren't solid structures like the arms of a starfish, but rather density waves, regions where stars, gas, and dust temporarily crowd together as they orbit the galactic center. Think of them as traffic jams on a cosmic highway. As material moves through these denser regions, it slows down slightly, creating the visible structure we see as spiral arms. The arms themselves don't rotate as solid objects. Instead, the density wave pattern rotates, while individual stars and gas clouds move through the arms over time, entering from one side and eventually emerging from the other. Within these arms, conditions favor star formation. Gas clouds collide and compress, triggering gravitational collapse. New stars ignite, illuminating the arms with brilliant blue light. This is why spiral arms appear so prominent in photographs. They're traced out by young, luminous stars that haven't yet had time to drift away from their birthplaces. The arms may also be reinforced by gravitational interactions with neighboring galaxies, or by resonances in the galaxy's rotation pattern. They're beautiful accidents of physics, emergent structures arising from the interplay of gravity, rotation, and density. And while spiral galaxies often capture our attention with their photogenic structure, they're not the only galactic architecture in the cosmos. Elliptical galaxies appear as smooth, round, or oval collections of older stars. Unlike spirals, they have no obvious structure, no spiral arms, no disk of active star formation. They're shaped like footballs or basketballs or eggs, depending on how elongated they are. Their stars move in complex, disordered orbits, some circling one way, some another, some plunging through the center and back out again in highly elliptical paths. There's very little gas or dust in elliptical galaxies, which means very little new star formation. The stars that populate them are mostly old, red, cool, suns that have been burning for billions of years. This gives elliptical galaxies a reddish or yellowish hue when we photograph them, quite different from the blue-white glow of spiral arms rich with young stars. Elliptical galaxies range enormously in size. Some dwarf ellipticals contain only a few million stars and are barely larger than globular clusters. Others are giants, containing trillions of stars and spanning hundreds of thousands of light years. These massive ellipticals often sit at the centers of galaxy clusters, where they've grown fat by consuming smaller galaxies over billions of years. They represent a different path in galactic evolution, one where the raw material for star formation has been exhausted or stripped away, leaving behind a smooth, aging stellar population. And while spirals and ellipticals dominate our classification schemes, some galaxies defy categorization altogether. Irregular galaxies have no defined shape, often distorted by gravitational interactions. They're the cosmic misfits, galaxies that don't fit neatly into the spiral or elliptical categories. Some are small, chaotic collections of stars, gas, and dust with no obvious structure at all. Others show hints of spiral arms or bar structures that have been warped and disrupted. Many irregular galaxies are that way because they've had close encounters with other galaxies. The gravitational tug from a passing neighbor can pull out long streams of stars, distort rotation patterns, trigger massive bursts of star formation. The result is a galaxy that looks chaotic, asymmetrical, sometimes featuring strange loops or tails of material extending far from the main body. Some irregular galaxies are rich in gas and actively forming stars, their chaotic appearance belying vibrant stellar nurseries within. Others are the remnants of galactic collisions, still settling into equilibrium after a dramatic encounter. The Large Magellanic Cloud, visible from the southern hemisphere as a bright patch in the night sky, is an irregular galaxy currently being torn apart by the Milky Way's gravity. Its distorted shape tells a story of gravitational interaction, of one galaxy slowly consuming another. Irregular galaxies remind us that cosmic order is temporary, that gravitational interactions shape and reshape galactic architecture over time. And among the spirals, some show a distinctive central feature. Barred spiral galaxies have a central bar-shaped structure, with arms extending from the ends. Instead of spiral arms emerging directly from a round central bulge, these galaxies have an elongated bar of stars running through their center, and the spiral arms begin at the ends of the bar. The bar is a real physical structure, not just a visual illusion, a region where stars and gas move in elongated orbits, creating a roughly rectangular or bar-like shape when viewed face-on. These bars aren't permanent fixtures. Computer simulations suggest they can form and dissolve over hundreds of millions of years, influenced by the galaxy's rotation pattern, its distribution of mass, and gravitational interactions with other galaxies. The bar can affect star formation patterns, channeling gas toward the center where it may fuel a central black hole or trigger bursts of stellar birth. Bars are actually quite common. About 2/3 of spiral galaxies show some evidence of a bar structure, though some bars are more prominent than others. The presence or absence of a bar tells us something about the galaxy's history and internal dynamics, about the subtle ways that gravity shapes galactic architecture over cosmic timescales. And this bar structure isn't just a curiosity observed in distant galaxies. The Milky Way is a barred spiral galaxy. For a long time, astronomers weren't sure. Observing our own galaxy's structure is difficult because we're embedded within it, like trying to see the shape of a forest while standing among the trees. But observations in infrared light, which can penetrate dust clouds, revealed a distinct bar structure running through the Milky Way's center. This bar is about 27,000 light-years long, composed of older red stars. Our Sun sits outside the bar in one of the spiral arms that curves away from the bar's end. This means that as the Milky Way rotates, the bar rotates too, and over millions of years the configuration of stars and gas shifts in response to this rotating gravitational feature. The bar influences gas flows in the inner galaxy, potentially funneling material toward the central supermassive black hole. It affects stellar orbits, creating resonances that help maintain the spiral arm structure. Knowing that we live in a barred spiral helps us understand our galactic home's dynamics and evolution. It places us in a specific context within the zoo of galactic types, and reminds us that our galaxy isn't just a static backdrop but a dynamic, evolving structure with its own architectural quirks. Between the clear categories of spiral and elliptical, there exists a transitional type. Lenticular galaxies sit between spiral and elliptical types. They have disc-like structures similar to spirals, but lack prominent spiral arms. They have central bulges of stars, and when viewed edge-on, they appear lens-shaped, hence the name lenticular, from the Latin word for lentil or lens. In photographs, they often look like smooth discs of stars, without the dramatic arm structure that makes spirals so visually distinctive. Lenticular galaxies share characteristics with both spirals and ellipticals. Like spirals, they have rotating disks. Like ellipticals, they contain mostly older stars with little ongoing star formation. They're often found in galaxy clusters, where interactions with other galaxies and with the hot gas that permeates the cluster may have stripped away most of their star-forming material. Some astronomers think lenticular galaxies represent an evolutionary stage. Perhaps they're spiral galaxies that have exhausted or lost their gas reserves, transforming into smoother, quiescent systems. Others suggest they form through specific types of galaxy mergers. Whatever their origin, they represent a significant fraction of galaxies in the universe, particularly in regions where galaxies are crowded together. They're a reminder that galactic taxonomy isn't a simple either-or proposition, that nature creates transitional forms and intermediate cases. And while massive galaxies dominate our attention, the universe is also full of much smaller galactic structures. Dwarf galaxies are much smaller, containing only millions to billions of stars. Where the Milky Way hosts hundreds of billions of stars, a dwarf galaxy might contain only a few million, tiny by galactic standards, yet each one still a vast collection of suns. These small galaxies come in various types: dwarf spheroidals, dwarf ellipticals, dwarf irregulars. Many orbit larger galaxies as satellites, held in place by gravity, slowly surrendering their stars to their larger companions over billions of years. Despite their small size, dwarf galaxies are important. They're thought to be among the first galaxies to form in the early universe, small clumps of stars that later merged to build larger structures. The Milky Way itself likely grew partly by consuming dwarf galaxies over cosmic time. Even today, we can see dwarf galaxies in the process of being torn apart, streams of stars pulled from these small satellites, spreading out along their orbits around the Milky Way. Dwarf galaxies also present cosmological puzzles. Theory predicts there should be far more of them than we observe, a discrepancy that hints at gaps in our understanding of dark matter or galaxy formation. But despite their modest size, they're full participants in the grand ecological system of galaxy evolution, both shaped by and shaping the cosmic structures around them. And some galaxies push the boundaries of faintness. Ultra-diffuse galaxies are extremely faint and spread out. They have roughly the same mass as dwarf galaxies, but their stars are spread across a much larger volume, making them so dim that they're incredibly difficult to detect. Imagine taking all the stars in a typical dwarf galaxy and scattering them across a region the size of the Milky Way. The result would be a galaxy so diffuse, so spread out that it's almost invisible, a ghostly presence barely distinguishable from the background sky. These ultra-diffuse galaxies were discovered only recently, as improved telescopes and detection techniques allowed astronomers to find objects that were previously too faint to notice. They're particularly common in galaxy clusters, and their existence raises questions about galaxy formation. How can a galaxy form with so little density? Why didn't it collapse into a more compact structure? Some theories suggest they might be failed, massive galaxies, systems that should have become larger but somehow didn't accrete enough material. Others propose they're normal galaxies that have been puffed up by tidal forces or by feedback from star formation. They challenge our understanding of what a galaxy can be, reminding us that the cosmos is full of subtle variations on the theme of gravitationally bound stellar systems. And sometimes, violent interactions create entirely new galactic structures. Ring galaxies form when one galaxy passes through the center of another. It's a cosmic bullseye, a dramatic demonstration of gravitational physics playing out on galactic scales. When a compact galaxy, often a small elliptical, plunges directly through the center of a larger disk galaxy, it creates a shock wave, a ripple of density that propagates outward through the disk. This density wave compresses gas clouds as it passes, triggering intense star formation. The result is a ring of bright, newly formed stars expanding outward from the impact point, while the central regions of the target galaxy appear relatively empty. The collision doesn't destroy either galaxy. Remember, stars are so far apart that they don't actually collide, but the gravitational disruption reshapes the larger galaxy dramatically. Ring galaxies are temporary structures, lasting perhaps 100 million years before the ring dissipates and the galaxy settles into a new equilibrium. They're rare, requiring a very specific type of collision, a direct hit through the center rather than a glancing blow or a slow merger. The most famous example is the Cartwheel Galaxy, which shows a bright outer ring and fainter inner rings, like ripples on a pond frozen in time. These systems offer astronomers a chance to study galaxy collisions in action, to watch in real time, albeit on astronomical timescales, the consequences of galactic encounters. And the colors of galaxies tell their own stories. Some galaxies appear blue because they're actively forming new stars. Blue light comes from hot, massive stars, the type that burn bright and die young, living only a few million years before exhausting their fuel and exploding as supernovae. When you see a galaxy glowing blue, you're looking at a population of these young, hot stars, which means you're looking at a galaxy where star formation is happening right now, in cosmic terms. These blue galaxies tend to be spirals or irregulars, types that still have abundant gas and dust available for making new stars. The spiral arms in particular often glow blue-white, traced out by recent stellar births. In contrast, galaxies dominated by older stars appear yellow or red. These are usually elliptical galaxies or lenticulars, where star formation has largely ceased. Their stellar populations are aging, and the brightest stars, the massive blue ones, have already died, leaving behind the cooler, redder, longer-lived stars. The colour of a galaxy is thus a window into its life cycle, a clue about whether it's still actively growing its stellar population or whether it's entered a quieter phase of evolution. And just as individual stars have life cycles, galaxies themselves have formation stories that stretch back to the universe's youth. Galaxies began forming a few 100 million years after the Big Bang. In the beginning, the universe was smooth, almost perfectly uniform, filled with hot gas cooling as space expanded. But almost makes all the difference. Tiny density fluctuations, quantum variations from the earliest moments of the universe, provided the seeds for structure. These slightly denser regions had slightly stronger gravity, pulling in surrounding material. Over millions of years, these small differences amplified. Gas flowed toward the denser regions, collecting in growing wells of dark matter. Eventually, enough gas accumulated for gravity to compress it, heating it until nuclear fusion ignited. The first stars flickered to life perhaps 100 to 200 million years after the Big Bang. These earliest stars were massive, short-lived, and they changed the universe. Their light ionized surrounding gas. Their deaths seeded space with heavy elements, and they clustered together, pulled by gravity, forming the first small galaxies. These proto-galaxies were nothing like the majestic spirals we see today. They were small, chaotic, barely more than large star clusters. But they were the beginning, the first structures to emerge from the cooling primordial gas, and they would be the building blocks of everything that came after. And these early structures didn't remain small. The earliest galaxies were smaller and merged over time to create larger ones. Galaxy formation wasn't a one-time event, but an ongoing process of growth through accretion and collision. In the early universe, small proto-galaxies formed in abundance, each containing perhaps millions of stars. But dark matter's gravity continued to work, pulling structures together. Small galaxies merged into larger ones. These larger systems consumed other small galaxies, growing in mass and complexity. Over billions of years, through countless mergers and accretions, the small chaotic systems of the early universe transformed into the grand spiral and elliptical galaxies we observe today. This hierarchical growth, small structures merging into larger ones, is a fundamental prediction of cosmological models, and observations of distant galaxies confirm it. When we look at galaxies as they were billions of years ago, we see smaller, more irregular, more chaotic systems. As we look closer to the present day, we see the emergence of ordered spirals and massive ellipticals. The Milky Way itself is a product of this process, assembled over billions of years from dozens or hundreds of smaller galaxies, each contributing their stars and gas to the growing whole. And this assembly process required a scaffolding invisible to our eyes. Dark matter provides the gravitational framework for galaxies to form. Ordinary matter, the stuff of stars and planets and people, makes up only about 15% of all matter in the universe. The rest is dark matter, a substance that interacts with normal matter only through gravity. We can't see it, can't detect it directly, yet its gravitational influence is unmistakable. Dark matter clumped together first, before ordinary matter had a chance to follow, creating gravitational wells, invisible structures that pulled in gas. These dark matter halos became the scaffolding on which galaxies built themselves. Without dark matter, the gravity of ordinary gas wouldn't have been strong enough to overcome the universe's expansion and collapse into galaxies, at least not in the time available. The universe would look completely different, perhaps empty of galaxies entirely, or at least much more sparsely populated. Every galaxy we observe is embedded in a halo of dark matter, typically extending far beyond the visible stars. The Milky Way's dark matter halo likely extends hundreds of thousands of light years into space, invisible but massive, providing the gravitational foundation that holds our galaxy together. Understanding dark matter remains one of astronomy's greatest challenges, a reminder that the visible universe is only a fraction of what exists. And within this dark matter framework, ordinary matter began its transformation. Gas clouds collapse under gravity to create the first stars in a galaxy. The process begins with a cloud of hydrogen and helium gas, perhaps seeded with tiny amounts of heavier elements from earlier stellar generations. This cloud sits within a dark matter halo, feeling the pull of gravity. If the cloud is large enough and dense enough, gravity begins to overcome the gas's internal pressure. The cloud contracts. As it contracts, it fragments into smaller clumps, each collapsing on its own. The process is beautifully complex, gas streaming inward, turbulence creating structure, magnetic fields threading through the collapsing material, sometimes opposing collapse, sometimes channeling it. Within the densest cores, temperatures rise as gravitational energy converts to heat. Eventually, in the center of a collapsing clump, conditions become extreme enough for nuclear fusion to ignite. A star is born. It begins to shine, its radiation pushing against surrounding gas, sometimes halting further collapse, sometimes triggering new waves of star formation in neighboring regions. The first stars in a young galaxy transform their environment. They produce heavy elements through fusion. When massive stars die in supernova explosions, they enrich the interstellar medium with carbon, oxygen, iron, the building blocks of planets and life. Each generation of stars changes the chemical composition of the galaxy, a process of enrichment that continues today, and this process of growth through merger and accretion continues across cosmic time. Galaxies grow by consuming smaller galaxies and gas from their surroundings. A large galaxy like the Milky Way doesn't exist in isolation. It's surrounded by smaller satellite galaxies, held in orbit by gravity, and over time, these satellites don't remain separate. Tidal forces, gravitational pulls that are stronger on the near side than the far side, gradually tear the satellite apart. Stars get stripped away, forming streams and shells around the larger galaxy. Eventually, the satellite is completely dissolved, its stars absorbed into the larger system. We see evidence of this process everywhere. The Milky Way has streams of stars in its halo, remnants of dwarf galaxies consumed in the past. The Sagittarius dwarf elliptical galaxy is being torn apart right now, its stars spreading around the Milky Way in a long, arcing stream. Andromeda shows similar features, shells and streams of stars from past meals. Beyond satellites, galaxies also accrete gas from the intergalactic medium, cool gas streams along cosmic web filaments, falling into the galaxy's gravitational well, providing fresh material for star formation. This steady diet of gas and smaller galaxies allows large galaxies to continue growing over billions of years, a process that hasn't stopped, that continues even in the present epoch. And understanding this process means looking at galaxy formation as an ongoing phenomenon. The process of galaxy formation continues today, just more slowly. We often think of galaxy formation as something that happened long ago, in the early universe, but it's not a finished process. Galaxies are still accreting gas, still consuming satellites, still occasionally merging with other large systems. The rate has slowed. The early universe was denser, with more raw material available, more frequent interactions between growing structures. Today, the universe has expanded, galaxies are more spread out, and the pace of formation and growth has decreased. But it hasn't stopped. Small galaxies are still falling into larger ones. Gas is still streaming onto galactic disks, fueling new generations of stars. In dense galaxy clusters, elliptical galaxies at the centers continue to grow, pulling in smaller galaxies that venture too close. Even the Milky Way continues to evolve, its structure slowly changing as it consumes dwarf galaxies and prepares for its eventual merger with Andromeda. Galaxy formation isn't an event that happened at a specific time in cosmic history, but an ongoing process, a continuous evolution driven by gravity and the distribution of matter across space. Observing this requires tools that can model the complexity of galactic evolution across billions of years. Computer simulations can recreate billions of years of galaxy evolution. Understanding how galaxies form and evolve requires more than observation. It requires theory, mathematical models, and computational power. Astronomers use supercomputers to simulate the behavior of millions or billions of particles representing stars, gas, and dark matter. They program in the laws of gravity, hydrodynamics, star formation, and feedback processes. Then they press play and watch billions of years of cosmic evolution unfold in fast forward. These simulations start with initial conditions based on observations of the early universe, a nearly smooth distribution of matter with tiny fluctuations. As the simulation progresses, these fluctuations grow. Dark matter clumps first, then gas follows. Stars form, evolve, die. Galaxies emerge, collide, merge. After billions of simulated years, the results can be compared with real observations. Do the simulated galaxies look like real ones? Do they have the right sizes, shapes, star formation rates? Discrepancies between simulation and observation reveal gaps in our understanding, pointing toward physics we've missed or modeled incorrectly. These simulations have become increasingly sophisticated, incorporating more detailed physics, tracking chemical evolution, modeling supermassive black hole growth. They're essential tools for testing theories, for understanding the complex web of processes that transform primordial gas into the structured galaxies we observe. And these simulations reveal that galaxies don't exist as isolated islands. The cosmic web shows how galaxies connect along vast filaments of dark matter. If you could zoom out and see the large-scale structure of the universe, you wouldn't see galaxies distributed randomly or uniformly. You'd see a web, filaments of galaxies stretching across hundreds of millions of light-years, connected at nodes where clusters form, separated by vast, empty regions. This is the cosmic web, the largest structure in the universe, and it traces the underlying distribution of dark matter. Dark matter collapsed first into this filamentary structure, and ordinary matter followed, flowing along the filaments like water through channels. Galaxies formed where the filaments intersected, where the concentration of matter was highest. Computer simulations and observational surveys both reveal this same pattern, a foamy web-like structure with galaxies strung along filaments like beads on cosmic strings. The Milky Way sits on one such filament. We can trace neighbouring galaxies stretching away from us in preferential directions, outlining the thread of the web we inhabit. This structure emerged naturally from the initial density fluctuations in the early universe, amplified by gravity over billions of years. It's a beautiful demonstration of how simple physical laws, acting over cosmic time and distance, can create order and structure from near uniformity. Between the bright filaments lie regions of profound emptiness. Voids exist between galaxy clusters, empty regions of space. These voids are enormous, some spanning hundreds of millions of light years across, and they're remarkably empty. Where galaxy clusters might contain thousands of galaxies packed into a relatively small volume, voids contain almost nothing. Perhaps a few small galaxies drift through these vast empty regions, but compared to the richness of clusters and filaments, voids are cosmic deserts. They're not completely empty of dark matter. Simulations suggest dark matter threads through voids at low density, but they're severely underdense compared to the cosmic average. These voids didn't form because matter was removed. Rather, they represent regions that were slightly less dense in the early universe. While denser regions collapsed and formed galaxies, these underdense regions expanded along with the universe's expansion, becoming progressively emptier as surrounding matter drained away toward denser regions. Voids are important for understanding cosmic structure. Their existence and properties constrain models of structure formation. The fact that they're not completely empty but contain some small galaxies tells us about how low-density regions evolve. And the shapes and sizes of voids reflect the initial conditions of the universe, the pattern of quantum fluctuations that seeded all subsequent structure. This cosmic web and its voids emerged from subtle variations present at the universe's beginning. Galaxy formation is influenced by the initial density fluctuations after the Big Bang. In the first moments after the Big Bang, quantum fluctuations in the inflating universe created tiny variations in density, regions slightly denser or slightly less dense than average, differing by only 1 part in 100,000. These fluctuations were imprinted on the cosmic microwave background radiation, which we can observe today as slight temperature variations across the sky. But tiny as they were, these fluctuations mattered. They became the seeds for all structure in the universe. Slightly denser regions had slightly stronger gravity, attracting more matter. This made them denser still, which strengthened their gravity further, a runaway process called gravitational instability. Over hundreds of millions of years, these tiny variations amplified into the cosmic web of galaxies and voids we see today. The pattern was set in those first moments. The blueprint for galaxy formation, written in quantum fluctuations smaller than an atom, expanded by inflation to span the observable universe. It's a profound connection. The largest structures in the cosmos, stretching across billions of light years, trace their origins to quantum uncertainty in the universe's first fraction of a second. And among all the galaxies that formed from these primordial seeds, one holds special significance for us. The Milky Way is about 13.6 billion years old. Our galaxy is nearly as old as the universe itself, which is approximately 13.8 billion years old. The Milky Way didn't form all at once. It assembled gradually from smaller structures that merged over time. But the oldest stars in the Milky Way's halo formed within a few 100 million years of the Big Bang. These ancient stars, composed almost entirely of hydrogen and helium, with barely a trace of heavier elements, are fossil records of the early universe. They tell us that the Milky Way's assembly began early, that the process of gathering matter and forming stars started soon after the first generation of structures emerged from the primordial gas. Over the following billions of years, the galaxy grew and evolved. The disk formed as gas settled into a rotating plane. The spiral arms emerged from density waves in the disk. Smaller galaxies merged with the growing Milky Way, adding their stars to our galactic family. The story of the Milky Way is a story of continuous evolution from small chaotic beginnings to the structured spiral we inhabit today. And within this vast structure, we occupy a particular location. Our solar system sits in a minor arm called the Orion Spur. The Milky Way's major spiral arms, Perseus, Scutum Centaurus, Norma, and Sagittarius, are the dominant structural features of the disk. But between these major arms lie smaller structures, sometimes called spurs or feathers, branches off the main spiral pattern. One of these is the Orion Spur, also called the Orion Arm or the local arm, and it's where we live. This minor arm extends between the Sagittarius and Perseus arms, a bridge of stars and gas about 10,000 light-years long and 3,500 light-years wide. Our solar system lies near the inner edge of this spur, in a relatively quiet stellar neighbourhood. We're not in the dense, crowded environment of the spiral arms proper, where massive stars are born and die in spectacular supernovae, where star formation is intense and the radiation environment can be harsh. Instead, we're in a calmer region, which may have implications for the development of life. Too close to active star-forming regions might expose a planet to dangerous radiation. Too far from the action might mean a shortage of heavy elements needed for rocky planets. Our location in the Orion Spur seems fortuitously mild, a cosmic suburb rather than an urban core or isolated countryside, and this location is a specific distance from the galaxy's center. We're located about 26,000 light-years from the galactic center. This distance places us roughly halfway between the center and the edge of the galactic disk, in what astronomers call the galactic habitable zone, a region where conditions might be favorable for life. Closer to the center, stellar density increases, supernova rates are higher, and the radiation environment is more intense. Farther out, heavy elements become scarcer, potentially making it harder for rocky planets to form. Our location provides a balance. We're far enough from the center to avoid most hazards, close enough that our solar system contains the elements necessary for planets and life. This distance also affects what we can see. Looking toward the galactic center, we see dense star fields, clouds of dust blocking our view in visible light, though infrared and radio telescopes can peer through. Looking away from the center toward the outer galaxy, the stars thin out, and we can see much farther into intergalactic space. Our perspective on the Milky Way is shaped by our position within it, observing from inside, trying to map a structure we can never step outside to view from afar. And from our vantage point, the Milky Way extends a tremendous distance in all directions. The Milky Way's stellar disk stretches across 150,000 to 200,000 light-years, even larger when including its dark matter halo. For decades, textbooks cited 100,000 light-years as the Milky Way's diameter, but improved observations, particularly from the Gaia spacecraft, have revised that upward. The visible disk of stars extends at least 150,000 light-years across, and some studies suggest 200,000 light-years or more, but that's just the stars. The Milky Way is much larger when you include all its components. The dark matter halo extends far beyond the stellar disk, perhaps several 100,000 light-years in all directions, creating a vast spherical structure that dominates the galaxy's total mass. Within this immense volume, most of the space is empty. Remember, the distances between stars are vast, but the overall structure is immense beyond comprehension. To cross the Milky Way at the speed of light would take 150,000 to 200,000 years. No human spacecraft will ever make such a journey. Even transmitted signals would require millennia to cross our galaxy. These scales humble us, reminding us of our smallness, yet also inspire wonder at our ability to measure and map structures so vastly larger than ourselves. At the heart of this vast disk lies a bulging concentration of stars. The Milky Way has a central bulge of older, reddish stars. If you could view the Milky Way edge-on from outside, you'd see a thin disk with a bright, swollen region at its center, the galactic bulge. This bulge is roughly 10,000 light-years across, composed primarily of old stars that formed billions of years ago. These stars are redder and cooler than the young blue stars in the spiral arms, giving the bulge a yellowish-red hue in photographs. The bulge is a crowded place by galactic standards. Stars are much closer together here than in the disk. If you stood on a planet orbiting a star in the bulge, the night sky would be magnificent. Thousands of stars bright enough to cast shadows, the sky never truly dark. The bulge probably formed early in the Milky Way's history, perhaps through mergers of smaller galaxies, or through instabilities in the early disk. It may contain a bar structure running through its center, and at the very heart of this bulge sits Sagittarius, a star, the Milky Way's supermassive black hole. The bulge represents the ancient core of our galaxy, a structure that formed when the universe was younger and star formation was more violent. And surrounding this central concentration, the stars are arranged in a relatively thin layer. The Milky Way's disk is relatively thin, only about 1,000 light-years thick. Compared to its diameter of 150,000 to 200,000 light-years, the disk is remarkably flat. Imagine scaling the Milky Way down to the size of a dinner plate. The plate would be perhaps 100 feet across, but only a fraction of an inch thick. That's the proportional thickness of the galactic disk. This flatness results from rotation. When the Milky Way was forming, the gas that would become the disk was rotating. As this gas collapsed under gravity, conservation of angular momentum dictated that it would flatten into a disk perpendicular to the rotation axis. Stars forming in this disk inherit its flat distribution. Some older stars have orbits that carry them high above or below the disk. These form the galactic halo. But most stars in the Milky Way, including our Sun, stay relatively close to the disk's plane. This thin structure makes the Milky Way vulnerable to perturbations. When a satellite galaxy passes through the disk, it can create ripples, waves in the stellar distribution that propagate outward like ripples on a pond. We see evidence of such waves in the Milky Way today, probably caused by a dwarf galaxy passing through relatively recently, in the past few 100 million years. Beyond the thin disk lies a more diffuse structure. The Milky Way has a halo of old stars and globular clusters surrounding it. If the disk is the Milky Way's body, the halo is its atmosphere, a vast, roughly spherical region extending perhaps 200,000 light-years from the galactic center. The halo is much less dense than the disk, containing perhaps only 1% of the Milky Way's total stellar mass, but it's important for understanding our galaxy's history. The halo is populated by old stars, some of the oldest in the galaxy, and by globular clusters, dense, spherical collections of hundreds of thousands of ancient stars. These globular clusters orbit the Milky Way on highly elliptical paths, plunging through the disk and then swooping out into the halo again. The stars in the halo formed early in the Milky Way's history, before the disk had fully assembled. Many may have originally been part of small satellite galaxies that were later torn apart, their stars scattered through the halo. The chemical composition of halo stars supports this picture. They contain very few elements heavier than hydrogen and helium, consistent with formation in the early universe when few supernovae had yet enriched space with heavy elements. The halo is a fossil record, preserving clues about the Milky Way's assembly and early evolution. And all these components, disk, bulge, halo, move in concert as the galaxy rotates. The Milky Way rotates at about 515,000 miles per hour at our position. This is our orbital velocity around the galactic center, the speed at which our entire solar system, including Earth, is moving through space relative to the Milky Way's center. We don't feel this motion, of course. There's no air to rush past, no landmarks to judge velocity against. But the motion is real, measurable through observations of how stars and gas move relative to each other. This rotation isn't like a solid body spinning. Different parts of the Milky Way rotate at different speeds. The rotation is differential. Near the center, orbital velocities are higher. Farther out, they decrease, but not as much as Newton's laws would predict based on visible matter alone. This flat rotation curve, the fact that stars far from the center move faster than expected, was one of the first strong pieces of evidence for dark matter. There must be additional mass we can't see, extending far from the galactic center, providing extra gravitational pull that keeps outer stars moving fast. And this rotation means that everything in the galaxy, including us, is constantly orbiting, endlessly circling the common center of mass. It takes our solar system roughly 230 million years to complete one orbit. This staggering timescale, called a galactic year or cosmic year, dwarfs human history. In the time humans have existed as a species, perhaps a few 100,000 years, we've completed only a tiny fraction of one orbit. When the last galactic year began, 230 million years ago, dinosaurs had not yet appeared. The supercontinent Pangaea was just beginning to form. Life on Earth was dominated by early reptiles and amphibians. When we complete our current orbit, 230 million years from now, Earth will be transformed in ways we can barely imagine. If humanity or its descendants still exist, they will have spread across the solar system, perhaps to other stars. Or perhaps life will have taken entirely different forms, adapted to conditions we can't predict. The galactic year reminds us of the immense timescales on which cosmic processes operate. Where human lifetimes measure decades, civilizations measure centuries or millennia, the galaxy operates on scales of hundreds of millions of years. And within the Milky Way's structure, stars of different ages coexist. The Milky Way contains multiple stellar populations of different ages. The oldest stars, formed within the first billion years of the galaxy's existence, are found primarily in the halo and in globular clusters. They're metal poor. Astronomers use metal to mean anything heavier than hydrogen and helium, because they formed before many generations of supernovae had enriched the interstellar medium. The bulge contains somewhat younger stars, though still ancient by human standards, formed perhaps 10 to 12 billion years ago. The disk has a mix, some old stars but also many younger ones, and star formation continues today in the spiral arms. Our Sun is middle-aged, about 4.6 billion years old, formed when the Milky Way was already well established. The youngest stars, just a few million years old, are found in active star-forming regions like the Orion Nebula. This mix of ages tells the story of ongoing star formation throughout the galaxy's history. The Milky Way didn't form all its stars in one burst and then stop. Instead, it has continuously recycled material, gas collapsing to form stars, stars living and dying, returning enriched gas to space, which collapses again to form new stars. Each generation adds new chemical elements to the mix, gradually increasing the metallicity of subsequent stellar populations. And looking beyond our own galaxy, we find neighbors that are approaching us. The Andromeda galaxy contains roughly 1 trillion stars, where the Milky Way has perhaps 200 to 400 billion stars. Andromeda, also called M31, is larger, containing an estimated 1 trillion suns. It's a giant spiral galaxy, the largest member of our local group, and in many ways similar to the Milky Way, though somewhat bigger. If you could see Andromeda's full extent with the naked eye, it would appear several times larger than the full moon in our sky. The galaxy is enormous, spanning more than 3 degrees across, but it's so faint that only its bright central core is visible without a telescope. Through a telescope, Andromeda reveals itself as a magnificent spiral, its disk tilted at an angle so we see it somewhat edge-on. We can discern its spiral arms, its central bulge, even some of its globular clusters and giant star-forming regions. We can measure its rotation, track individual bright stars within it, observe supernovae exploding in its disk. Andromeda is close enough that we can study it in detail, learning lessons applicable to galaxies throughout the universe, yet far enough that we see it as a coherent whole, not embedded within it as we are with the Milky Way. And under dark skies, this neighboring galaxy is visible to the unaided eye. Andromeda appears as a faint smudge to the naked eye in dark skies. Away from city lights, on a moonless autumn night in the northern hemisphere, you can see it, a small fuzzy patch in the constellation Andromeda, distinctly different from the sharp points of stars. Ancient astronomers recorded it as a little cloud, not understanding what they were seeing. It wasn't until the 1920s that Edwin Hubble, using the 100-inch telescope on Mount Wilson, resolved individual stars in Andromeda and proved that it was a galaxy beyond the Milky Way, an island universe in its own right. That faint smudge you can see with your naked eye is the light of 1 trillion stars, photons that have traveled 2.5 million years across the void to reach your eye. You're seeing Andromeda not as it is now, but as it was when our human ancestors were just beginning to evolve in Africa. The light carries information about Andromeda's past, and when we collect that light with telescopes and analyze it carefully, we discover that Andromeda isn't staying put, it's moving toward us. Andromeda is approaching us at about 250,000 miles per hour. While the universe's expansion carries distant galaxies away from us, Andromeda is close enough that the mutual gravitational attraction between our galaxies overcomes the expansion. We're pulling on Andromeda, and Andromeda is pulling on us, and the result is that the gap is closing. The approaching velocity seems enormous by everyday standards. 250,000 miles per hour is fast enough to circle Earth in about 6 minutes, but on the scale of galactic distances, it's not particularly remarkable. At this speed, closing the 2.5 million light-year gap will take about 4.5 billion years. That seems like a vast time, and it is, but it's less than the age of Earth. When Andromeda and the Milky Way finally encounter each other, our sun will still be shining, though significantly brighter than today as it ages. If humans or their descendants still exist, they'll witness a spectacle unfolding over millions of years, another galaxy growing larger in the sky, eventually dominating the night with thousands of bright points where we now see only the faint smudge of Andromeda's core. And this approach leads to an inevitable conclusion. The Milky Way and Andromeda will merge in about 4.5 billion years. This collision is inevitable, barring some unforeseen change in the galaxy's trajectories. Computer simulations can model what will happen, and while details vary depending on exact parameters, the general picture is clear. First encounter will occur in roughly 4.5 billion years. The galaxies will pass through each other. Remember, stars are so far apart that actual stellar collisions are virtually impossible. But gravitational interactions will be dramatic. Both galaxies will be distorted, pulled into strange shapes by tidal forces. The collision will trigger bursts of star formation as gas clouds collide and compress. After the first pass-through, the galaxies won't separate cleanly. Gravity will pull them back together. They'll collide again and again in a chaotic dance, lasting perhaps another billion years. Gradually, the orbital energy will dissipate through dynamical friction, and the two galaxies will settle into a new configuration. The merger will scramble stellar orbits, disrupting both galaxies' structures completely. And from this chaotic collision, a new type of galaxy will emerge. When they merge, they'll form a giant elliptical galaxy. The ordered spiral structures of both the Milky Way and Andromeda will be destroyed in the merger. Spiral arms will be torn apart, disks disrupted, stars scattered onto random orbits. The resulting galaxy will likely be a large elliptical, a smooth, featureless collection of stars with no disk, no spiral arms, just a huge ellipsoidal swarm of stars orbiting the common center. Astronomers have nicknamed this future galaxy Milkomeda or Milkdromeda, though of course no human will be around to call it anything. The merger will dramatically alter the night sky as seen from any surviving planets. Stars will be brighter and more numerous in the sky as the merged galaxy's density increases in some regions. The supermassive black holes at the centers of both galaxies will eventually merge, creating an even larger black hole. Star formation, triggered by gas compression during the collision, will gradually fade as the available gas is consumed or expelled. The resulting elliptical will be a quieter, older galaxy, having exhausted most of its star-forming potential during the violent merger. And while the Milky Way and Andromeda are the two dominant galaxies in our neighborhood, they're not alone. The Triangulum galaxy is the third largest in our local group. Also known as M33, Triangulum is a spiral galaxy located about 2.7 million light-years from Earth, making it slightly more distant than Andromeda, but still a member of our local family of galaxies. It's smaller than the Milky Way or Andromeda, containing perhaps 40 billion stars, but it's still a substantial galaxy in its own right. Under exceptionally dark skies, Triangulum is just barely visible to the naked eye as an extremely faint smudge, one of the most distant objects visible without optical aid. Through telescopes, it reveals itself as a face-on spiral with well-defined arms and active star-forming regions. Triangulum is bound gravitationally to the Milky Way and Andromeda, and it too will eventually participate in the grand merger. Whether it collides first with Andromeda or the Milky Way, or waits until after they've merged, depends on precise details of its orbit that are still being determined. But its fate is sealed. Within several billion years, Triangulum will be absorbed into the larger structure, its stars adding to the giant elliptical that will eventually form. And beyond these three major spirals, our local group contains many smaller members. The local group contains more than 50 galaxies. When we map the galaxies in our immediate cosmic neighbourhood, within about 10 million light-years, we find dozens of them, though only 3 are large spirals. The rest are dwarf galaxies of various types: dwarf ellipticals, dwarf spheroidals, dwarf irregulars. Many are satellites of the Milky Way or Andromeda, orbiting the larger galaxies like moons around a planet. The Milky Way alone has dozens of known satellite galaxies. Though many are so faint, they're incredibly difficult to detect. New ones are discovered regularly as surveys become more sensitive. These dwarf galaxies range in size from millions to billions of stars, large structures in absolute terms, yet tiny compared to the major spirals. Some, like the Magellanic Clouds, are relatively bright and were known to ancient astronomers in the southern hemisphere. Others are so faint, so diffuse, they were discovered only in the 21st century. The local group is gravitationally bound. The galaxies within it are not being carried apart by cosmic expansion. Instead, they orbit each other, interact, merge over time. It's a dynamic family, constantly evolving, and it represents our cosmic neighbourhood, the galaxy cluster we call home. Most local group galaxies are dwarf galaxies orbiting larger ones. Of the 50+ galaxies in the local group, only 3 are large spirals. The rest are small, and most of those orbit either the Milky Way or Andromeda. These satellites are held in place by the larger galaxy's gravity, orbiting on timescales of hundreds of millions to billions of years. Some satellites are relatively close, like the Sagittarius dwarf elliptical, which is currently passing through the Milky Way's disk. Others orbit at greater distances, hundreds of thousands of light-years away, at the edges of the larger galaxy's dark matter halos. The relationship between large galaxies and their satellites is complex. The satellites are slowly being destroyed by tidal forces, their stars gradually stripped away and absorbed into the larger galaxy. Yet new satellites can also be captured if a small galaxy wanders too close. The satellite system around a large galaxy is thus constantly changing, a dynamic population shaped by gravitational interactions. The Milky Way's satellites help us understand dark matter, galaxy formation, and chemical evolution. Many contain very old, metal-poor stars, making them fossil records of early galaxy formation. And some satellites are particularly prominent in Earth's sky. The large and small Magellanic Clouds are dwarf galaxies visible from the southern hemisphere. These 2 irregular galaxies are the most prominent satellites of the Milky Way, visible to the naked eye as bright cloudy patches in the southern night sky. They were known to southern cultures for millennia and became known to European astronomers during the Age of Exploration, named after Ferdinand Magellan, though he wasn't the first European to record them. The Large Magellanic Cloud, or LMC, is about 160,000 light-years away and contains perhaps 30 billion stars. The Small Magellanic Cloud, or SMC, is slightly more distant at 200,000 light-years and smaller with maybe 7 billion stars. Both are irregular galaxies lacking the ordered structure of spirals, though the LMC shows hints of a bar structure. They're rich in gas and actively forming stars. The Tarantula Nebula in the LMC is one of the most active star-forming regions known, a massive stellar nursery visible even from our great distance. The Magellanic Clouds have been important to astronomy. They're close enough to study individual stars, yet far enough to see as coherent structures. They've hosted observable supernovae, and they're connected to the Milky Way by a stream of gas called the Magellanic Stream, evidence of their ongoing gravitational interaction with our galaxy. The Magellanic Clouds are slowly being consumed by the Milky Way's gravity. The gravitational tug-of-war between the Milky Way and these two dwarf galaxies is gradually tearing them apart. The Magellanic Stream, a vast arc of neutral hydrogen gas extending more than 100 degrees across the sky, is material that's been stripped from the clouds during their orbit around the Milky Way. This stream contains enough gas to make several million stars, all pulled from the clouds over the past few billion years. As the clouds continue their orbit, more material will be stripped away. Eventually, perhaps a few billion years from now, they may be completely dissolved, their stars scattered through the Milky Way's halo, their gas absorbed into our galaxy's star-forming disk. This process, large galaxies consuming smaller ones, is fundamental to galactic evolution. The Milky Way has grown partly through such cannibalism, and the Magellanic Clouds are simply the most recent and visible example of this ongoing process. When we look at them, we're watching galactic evolution in action, witnessing the slow destruction of satellite galaxies that will eventually add their material to our own. And looking beyond our local group, we can observe galaxies at much greater distances. The most distant galaxies we can see existed when the universe was very young. When we point our most powerful telescopes at the sky and expose for hours or days, collecting every possible photon, we can detect galaxies so distant that their light has traveled more than 13 billion years to reach us. These galaxies aren't nearby as they are now. We have no way of seeing their current state. Instead, we see them as they were more than 13 billion years ago, when the universe itself was less than a billion years old. These distant young galaxies look different from modern ones. They're smaller, more compact, less organized. They haven't had time to grow large through mergers. They're often blue, rich in young stars, star formation proceeding at prodigious rates. Some are chaotic, their structures irregular, still in the process of assembling. Looking at these distant galaxies is like looking through a time machine. The farther we look, the further back in time we see, and these most distant galaxies show us what the universe looked like when it was young, when galaxy formation was just beginning, when the first large structures were emerging from the primordial gas. And the journey of light from these galaxies to us tells its own story. Light from the farthest galaxies has traveled for over 13 billion years to reach us. Imagine a photon emitted from a star in one of these early galaxies, 13 billion years ago. It begins its journey through space, traveling at the speed of light, crossing the vast distances between stars, between galaxies. As it travels, the universe continues to expand around it, stretching space itself, lengthening the photon's wavelength gradually over billions of years. It passes through intergalactic space, mostly empty, occasionally encountering a stray atom of hydrogen or being deflected slightly by gravitational fields. For 13 billion years it travels, crossing distances almost beyond comprehension. Galaxies form and evolve along its path. Stars are born and die. On one unremarkable rocky planet orbiting an ordinary star in an ordinary galaxy, life emerges, evolves, eventually produces beings capable of building telescopes. And finally, after 13 billion years of travel, that photon enters a telescope aperture, focused onto a detector, its energy recorded as a single data point among billions. From that photon, and countless others like it, we reconstruct an image of a galaxy that existed when the universe was young, and we learn about cosmic history. And special photographic surveys have revealed just how many of these distant galaxies exist. The Hubble Deep Field images revealed thousands of galaxies in a tiny patch of sky. In 1995, astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky in the constellation Ursa Major. a region about 1/30,000th the diameter of the full moon. They exposed for many hours over 10 days, collecting as much light as possible from this tiny, dark region. When they processed the data, they found not emptiness, but thousands of galaxies, about 3,000 in that tiny field alone. Some were nearby spirals and ellipticals, but many were distant, faint smudges, galaxies billions of light years away, some appearing as they were more than 10 billion years ago. This was revelatory. If a random tiny patch of seemingly empty sky contained thousands of galaxies, then the entire sky must contain billions of galaxies, perhaps hundreds of billions. Subsequent surveys, the Hubble ultra-deep field, the extreme deep field, pushed even deeper, finding galaxies at even greater distances, revealing the universe's richness. These images changed our understanding of the universe's scale. They showed that galaxies are not rare, special structures, but ubiquitous, filling space in every direction as far as we can see. And the light from these distant galaxies carries a telltale signature. Some distant galaxies appear red-shifted because the universe's expansion stretches their light. As light travels through expanding space, its wavelength gets stretched along with space itself. Light that was emitted as blue or ultraviolet can be stretched to red or even infrared wavelengths by the time it reaches us. This is called cosmological redshift, and it's different from the Doppler shift caused by motion through space. It's a stretching of space itself, carrying the photon along for the ride. The more distant the galaxy, the longer its light has travelled, and the more expansion has occurred during that journey, so the greater the redshift. Astronomers use redshift as a distance indicator. Measuring how much a galaxy's light has been stretched tells us how far away it is and how long ago the light was emitted. The most distant galaxies have enormous redshifts, their visible light stretched into the infrared, requiring specialized detectors to observe. These high redshift galaxies are the youngest galaxies we can see, observed when cosmic evolution had only just begun. Early galaxies were smaller, bluer, and more chaotic than modern ones. When we observe galaxies at high redshift, seeing them as they were billions of years ago, they don't look like today's majestic spirals and massive ellipticals. They're smaller, typically containing fewer stars, distributed across smaller volumes. They're bluer, rich with young, hot stars, star formation proceeding at rates much higher than in modern galaxies, and they're more chaotic, lacking the orderly rotation patterns and well-defined structures of their descendants. Many appear clumpy, with bright knots of star formations scattered through irregular shapes. This makes sense given what we know about galaxy evolution. These early galaxies were still in the process of assembling, still accreting gas, still experiencing the mergers that would build them into larger systems. They hadn't yet settled into equilibrium configurations. They represent galaxies in their youth, energetic, messy, rapidly changing. As time passed, as they merged and grew and exhausted their gas supplies, they evolved into the more structured, quiescent galaxies we see nearby in the present-day universe. Observations of these early galaxies help us understand how that transformation occurred, and new telescopes continue to push the boundaries of what we can observe. The James Webb Space Telescope can see even more distant galaxies than Hubble. Launched in 2021, the James Webb Space Telescope was designed specifically to observe the early universe. Its large mirror and infrared sensitivity allow it to detect light that has been redshifted beyond visible wavelengths, light from galaxies so distant that Hubble could barely detect them or couldn't see them at all. Webb has already discovered galaxies that existed just a few 100 million years after the Big Bang, pushing our view of galaxy formation to earlier times than ever before. These observations are revealing surprises. Some early galaxies appear more massive and more structured than theories had predicted, suggesting our models of early galaxy formation may need revision. Webb can also study the detailed spectra of distant galaxies, determining their chemical compositions, star formation rates, and physical conditions in ways that were impossible before. Over its planned decade-long mission, Webb will revolutionize our understanding of how galaxies formed and evolved in the early universe, filling in details that were previously hidden from view. And some galaxies it observes date to times we could previously only theorize about. Some galaxies are so far that we see them as they were when the universe was less than 1 billion years old. The universe is about 13.8 billion years old. The most distant galaxies we've detected existed when the universe was only 400 to 500 million years old, less than 4% of its current age. Observing these galaxies is like seeing baby pictures of cosmic structure, catching galaxy formation in the act. At these early times, the universe was still emerging from the so-called Dark Ages, a period after the Big Bang when the universe had cooled enough for neutral hydrogen to form, but before the first stars and galaxies reionized that hydrogen. The first galaxies formed during or just after this transition, their starlight beginning to illuminate and ionize the surrounding neutral hydrogen. These earliest galaxies were the universe's first lights, the first beacons in the primordial darkness. They were small, but their influence was enormous. They began the process of transforming the universe from a dark, neutral place into the ionized, transparent medium we observe today. Every new discovery of galaxies at these extreme distances pushes back the frontier of our knowledge, and these observations serve a profound purpose in astronomy. Distant galaxies help us understand how the universe has evolved. Every galaxy we observe at a different distance is like a snapshot from a different time in cosmic history. Nearby galaxies show us the present-day universe. Galaxies at moderate distances, a few billion light-years away, show us the universe as it was a few billion years ago, when star formation rates were higher, when galaxy mergers were more common. Very distant galaxies show us the early universe, when the first structures were forming. By comparing galaxies at different distances, different epochs, we can trace how galaxy properties have changed over time. We can see how star formation rates have declined as the universe has aged and gas has been consumed. We can observe how galaxy mergers have built larger structures from smaller ones. We can track how chemical abundances have increased as successive generations of stars have enriched the interstellar medium. We can watch the cosmic web emerge from smaller structures. In essence, by looking at different distances, we're doing archaeology, reconstructing the history of the universe by observing its components at different stages of evolution. And the most distant galaxies occupy a special place in this cosmic timeline. The furthest galaxies exist near the edge of the observable universe. There's a limit to how far we can see, not because space ends, but because light hasn't had time to reach us from farther away. The observable universe has a radius of about 46 billion light-years, larger than 13.8 billion light-years, because space has been expanding while light travelled toward us. The most distant galaxies we can detect are approaching this observational horizon. Beyond them, there are certainly more galaxies, but their light hasn't reached us yet, and depending on the universe's expansion rate, it may never reach us. These furthest galaxies are the oldest we can observe, existing when the universe was in its infancy. They're also moving away from us faster than nearby galaxies due to cosmic expansion. The space between us and them is expanding at an accelerating rate. This creates a strange situation. We can see these galaxies because their light was emitted long ago when they were closer, but if we could see them as they are now, they would be even further away, and the light they're emitting now may never reach us. They represent the edge of our observable universe, the limit of what we can ever hope to see. And in seeing these distant galaxies, we're seeing light that has a particular relationship with time. We see distant galaxies not as they are now, but as they were long ago. This is one of the most profound and strange aspects of observing the cosmos. When we look at Andromeda, we see it as it was 2.5 million years ago. When we look at a galaxy 1 billion light years away, we see it as it was 1 billion years ago. That galaxy as it exists now, its current state, is invisible to us. The light showing us its present condition hasn't arrived yet, and won't arrive for another billion years. In a very real sense, the farther we look into space, the farther we look back in time. Our view of the universe is not of a single moment, but of layered time. Nearby objects nearly as they are now, distant objects as they were billions of years ago. This means we can never see the entire universe as it exists in a single moment. We're always looking at a patchwork of different times, near and far, present and past, mixed together in our telescopic views. It's a strange consequence of light's finite speed and the universe's vast distances, but it's also a gift. It allows us to observe cosmic history directly, to see not just what the universe is now, but what it was at different stages. And sometimes, observations reveal that galaxies don't always remain isolated islands. Galaxies collide and merge throughout cosmic time. Despite the vast distances between galaxies, collisions are not rare. In dense galaxy clusters where hundreds of galaxies orbit within a relatively small volume, close encounters happen frequently. Even in less crowded regions, galaxies wandering through space occasionally cross paths with neighbours, drawn together by gravity. When galaxies collide, the result is dramatic but slow by human standards. The collision unfolds over hundreds of millions of years, fast on cosmic timescales, but far too slow to observe in real time. We see many galaxies in various stages of merger, pairs just beginning to interact, systems in the chaos of collision, galaxies settling into new configurations after merging. These mergers are essential to galaxy evolution. They're how small galaxies grow into large ones, how spiral galaxies can transform into ellipticals, how supermassive black holes pair up and potentially merge. Collisions trigger star formation, redistribute stars and gas, fundamentally alter galactic structure. The Milky Way's future collision with Andromeda is just one example of a process that has been happening throughout the universe since the first galaxies formed. And despite the violence of these collisions, one aspect remains remarkably safe. Despite containing billions of stars, galaxy collisions involve virtually no stellar collisions. The distances between stars are so vast that direct impacts are essentially impossible. When two galaxies collide, billions of stars pass through the interaction zone, but the probability of any two stars actually hitting each other is extraordinarily small, effectively zero. Stars are tiny compared to the spaces between them. If you scaled the Sun down to the size of a grain of sand, the nearest star would be several miles away. On this scale, galaxies colliding would be like two clouds of sand grains, each grain miles from its neighbours, drifting through each other. The grains would pass by without touching. So, while galaxy collisions are violent in terms of gravitational disruption, Stars get flung onto new orbits, gas clouds collide and compress, structures are torn apart, individual stars glide past each other unharmed. If you were on a planet orbiting a star during a galactic collision, you might see the night sky gradually fill with more stars as the other galaxy's stars mixed with your own. But your sun and planet would be unaffected by direct collision. The violence is gravitational and large-scale, not intimate and destructive at the stellar level. And yet, these collisions do have dramatic effects on star formation. Galaxy collisions can trigger intense bursts of star formation. Though stars don't collide, gas clouds do. Galaxies contain vast reservoirs of cool molecular gas, distributed in clouds throughout their disks. When two galaxies collide, these gas clouds smash into each other at high velocities. Gas doesn't pass through gas the way stars pass between stars. It collides, compresses, shocks, and heats. This compression can trigger gravitational collapse, creating conditions for rapid star formation. Regions that might have taken millions of years to slowly form stars can suddenly burst into activity, creating thousands of new stars in a short time. The result is called a starburst, a period of exceptionally high star formation rate, sometimes hundreds of times higher than in normal galaxies. Starburst galaxies are very bright, glowing with the combined light of millions of young hot stars. They're also dusty. Dust grains heated by starlight emit in the infrared, making starburst galaxies among the brightest infrared sources in the sky. These starbursts are temporary, lasting perhaps tens of millions of years before the available gas is consumed or blown away by stellar winds and supernovae. But during their brief existence, they dominate the galaxy's light and fundamentally alter its future evolution by converting gas into stars at prodigious rates. And we can observe many examples of galaxies currently undergoing this process. The antennae galaxies are two spiral galaxies currently colliding. Located about 45 million light-years away in the constellation Corvus, this pair of galaxies is one of the nearest and youngest examples of a galaxy merger we can observe. They're named for the two long tidal tails of stars and gas that stream away from the main bodies, resembling an insect's antennae. These galaxies began colliding about 600 million years ago, recent by cosmic standards, and they're currently in the most active phase of interaction. Their cores are approaching each other, spiral structures disrupted, and the collision has triggered massive star formation throughout both galaxies. Hubble images reveal over 1,000 bright young star clusters formed during the merger, each cluster containing hundreds of thousands of stars. The antennae galaxies glow brightly in infrared and radio wavelengths, signatures of vigorous star formation and supernovae. Eventually, perhaps 400 million years from now, the two galactic nuclei will merge, and the combined system will begin settling into a new structure, likely an elliptical galaxy, the spiral forms of both progenitors lost forever. The antennae galaxies let us observe galactic collision physics in detail, serving as a local laboratory for understanding merger dynamics, and these collisions can produce some very distinctive visual features. Colliding galaxies can have their shapes dramatically distorted. The gravitational forces during a galaxy collision are complex and asymmetric, pulling on different parts of each galaxy with different strengths. The result can be spectacular deformations. Spiral arms get stretched and pulled out. Tidal tails, long streams of stars and gas, can extend hundreds of thousands of light-years from the main bodies, drawn out like taffy by differential gravitational forces. Bridges of material can form between the two colliding galaxies, connecting them with streams of stars. the orderly rotation of spiral galaxies gets disrupted, stars scattered onto chaotic orbits. Sometimes the collision creates shells, concentric ripples of stars surrounding the merged core, like ripples on a pond frozen in place. These distortions are temporary on cosmic timescales. Over hundreds of millions of years, the merged system will relax, stars settling into new equilibrium orbits, and the strange shapes will fade. But for a brief window, brief by cosmic standards, the collision creates visual drama, galaxies twisted into shapes that bear little resemblance to the orderly spirals or smooth ellipticals we're familiar with. These peculiar galaxies captured astronomers' attention long before their nature was understood, and the tidal tails deserve special mention for their beauty and physics. Tidal tails, long streams of stars, often form during galactic mergers. When galaxies collide, tidal forces, gravitational pulls that are stronger on the near side than the far side, can pull material out of both galaxies, creating long streamers. These tidal tails can stretch for hundreds of thousands of light years, arcing through space like cosmic ribbons. They're composed of stars, gas, and dark matter, drawn from the colliding galaxy's outer regions where gravitational binding was weakest. The formation of tidal tails is well understood through computer simulations. As two galaxies approach, the tidal force on one galaxy pulls more strongly on its near side, while the far side lags behind. This differential force stretches the galaxy, and material on both the leading and trailing edges can be pulled free, forming two tails. The exact shape and length of the tails depend on the galaxy's masses, their relative velocities, and the geometry of their collision. Some tidal tails are relatively short and stubby, others extraordinarily long and graceful. Over time, the stars in tidal tails don't remain in neat streams. They disperse, eventually forming part of the merged galaxy's halo. But for tens or hundreds of millions of years, they remain visible as elegant traces of gravitational interaction. And many galaxies show evidence that they've experienced multiple such events. Some galaxies show evidence of multiple past mergers. When we examine galaxies in detail, we often find clues to their history. Stellar populations of different ages and chemical compositions, suggesting they originated in different progenitor galaxies. Streams and shells of stars in the halo, remnants of tidally disrupted satellites, misaligned gas disks indicating recent accretion, central supermassive black holes more massive than expected, suggesting they grew through mergers with other black holes. The Milky Way itself shows evidence of past mergers. Its halo contains streams of stars that were once separate dwarf galaxies, now torn apart and scattered. Chemical analysis of stars reveals different populations that likely formed in different environments. The Milky Way's history is one of continuous growth through cannibalism, consuming smaller galaxies, growing larger and more massive over time. Many elliptical galaxies show even clearer evidence of multiple mergers. Their complex stellar populations, sometimes with kinematically distinct cores, suggest assembly from several progenitors. In dense galaxy clusters, the central giant ellipticals have likely grown through dozens or hundreds of mergers over billions of years, becoming truly massive systems. Each merger leaves signatures, and astronomers are learning to read these clues, reconstructing galactic family trees from the forensic evidence preserved in stellar orbits and chemical abundances. And mergers come in different scales. Major mergers can transform spiral galaxies into elliptical ones. When two spiral galaxies of comparable mass collide, the result is typically an elliptical galaxy. The orderly rotation of the spiral disks is disrupted, stars are scattered onto random orbits. The gas, compressed during the collision, forms stars in a burst, exhausting the fuel for future star formation. What emerges is a smooth, roughly ellipsoidal collection of stars with no disk, no spiral arms, just a featureless elliptical profile. This transformation is well documented through observations of merging systems at various stages and confirmed by computer simulations. The pathway from spiral to elliptical through major merger is a key component of galaxy evolution models. It helps explain why elliptical galaxies are more common in dense galaxy clusters, where mergers are frequent, while spirals dominate less crowded regions. It also explains why elliptical galaxies tend to be redder and have older stellar populations. The gas needed to form young blue stars was mostly consumed during the merger-induced starburst, leaving behind only older stars. Not all collisions are equal, though. Minor mergers, where a small galaxy collides with a much larger one, produce different outcomes, and these minor interactions are far more common. Minor mergers occur when a small galaxy is absorbed by a larger one. If a dwarf galaxy wanders too close to a massive spiral, the outcome is very different from a major merger between equals. The dwarf is tidally disrupted, its stars gradually stripped away and absorbed into the larger galaxy. The process can take billions of years. The dwarf's orbit decays slowly, each pass through the larger galaxy's disk, pulling more stars free, until eventually nothing remains of the original satellite but a stream of stars scattered through the larger galaxy's halo. The large galaxy is relatively undisturbed. It doesn't transform into an elliptical. Its spiral structure might show some warping or thickening, but the basic form persists. This minor merger scenario is extremely common. Most large galaxies are continuously consuming satellites. The Milky Way is currently in the process of minor mergers with several dwarf galaxies, including the Sagittarius dwarf. Over the Milky Way's history, it has likely absorbed dozens or hundreds of small satellites, each contributing a small fraction of its current stellar mass. Minor mergers are a gentle, continuous form of galaxy growth, contrasting with the violence of major mergers. They allow galaxies to grow without fundamentally restructuring, adding mass while preserving overall morphology. And while mergers occur at certain rates in the present universe, some galaxies stand out for their extreme activity. Some galaxies have extremely bright centers powered by supermassive black holes. While most galaxies host supermassive black holes at their centers, in some galaxies these black holes are actively feeding, accreting matter at tremendous rates. As material spirals toward the event horizon, it forms an accretion disk, heating to millions of degrees through friction and compression. This disk radiates enormous amounts of energy across all wavelengths: radio, infrared, visible, ultraviolet, X-rays, even gamma rays. The energy output can exceed that of all the stars in the galaxy combined, despite coming from a region smaller than our solar system. These active galactic nuclei, or AGN, are some of the most luminous objects in the universe. They were more common in the early universe when gas was more abundant and galaxy interactions more frequent, providing fuel for black hole growth. Today, they're less common, but they still play important roles in galaxy evolution. The energy and radiation from an AGN can heat gas throughout the galaxy, preventing it from cooling and forming stars, a process called feedback. This can regulate star formation, transforming star-forming spirals into quiescent ellipticals. AGN come in different types depending on our viewing angle and the black hole's activity level, and the most extreme types have their own classification. Quasars are the brightest type of active galaxy. The name stands for quasi-stellar radio source, given when these objects were first discovered in the 1960s. They appeared star-like in optical images, point sources rather than extended galaxies, but they had strange spectra and strong radio emission. It took years to realize that quasars were incredibly distant galaxies with extraordinarily luminous centers, so bright that the central AGN outshined the entire surrounding galaxy. A typical quasar can be 1,000 times more luminous than the Milky Way. Its light dominated by the accretion disk around a supermassive black hole consuming matter at prodigious rates. Quasars can be visible across billions of light years, beacons that allow us to study the early universe. They're powered by black holes, typically 1 billion times more massive than the Sun, growing rapidly through accretion. The fact that such massive black holes existed when the universe was young, some quasars are observed when the universe was less than 1 billion years old, is still puzzling to theorists. How did black holes grow so massive so quickly? Understanding quasar physics and evolution is key to understanding the co-evolution of galaxies and their central black holes. And quasars were particularly important in earlier cosmic epochs. Quasars were more common in the early universe. When we survey the sky for quasars, we find that they were most abundant when the universe was about 20 to 30% of its current age, roughly 10 billion years ago. At that epoch, galaxy mergers were more common, gas was more plentiful, and conditions favoured rapid black hole growth. As we look at more recent times, quasar numbers decline. In the nearby universe, true quasars are rare. Most supermassive black holes are either dormant or feeding at much lower rates. This evolution reflects changes in the universe's structure and gas supply. In the early universe, galaxies were closer together, mergers were frequent, and these mergers funneled gas toward galactic centers, feeding black holes. As the universe expanded and galaxies spread out, as galaxies exhausted their gas supplies through star formation and AGN feedback, the fuel for quasar activity diminished. Today's supermassive black holes are mostly quiescent, starved of material. The Milky Way's central black hole, for instance, is nearly dormant. It glows faintly from a trickle of infalling matter, nothing like a quasar. The quasar era was a phase in cosmic history when black holes grew rapidly, shaping their host galaxies through powerful feedback. And that era has largely passed. But quasars aren't the only type of active galaxy that produces dramatic phenomena. Jets of material can shoot out from active galactic nuclei at nearly the speed of light. In some AGN, particularly those with rapidly spinning black holes, material doesn't just fall inward, some of it gets channeled along magnetic field lines and ejected perpendicular to the accretion disk. These jets are among the most powerful phenomena in the universe. Narrow beams of plasma accelerated to speeds approaching that of light, extending sometimes for hundreds of thousands or even millions of light years beyond the galaxy. The physics of jet formation is complex, involving magnetic fields, black hole spin, and the properties of the accretion disk. The jets carry enormous amounts of energy, and when they slam into the surrounding intergalactic medium, they create shock waves, heating gas and creating enormous radio-emitting lobes visible in radio telescope images. These jets can affect the entire galaxy and beyond, ploughing through gas that might otherwise form stars, regulating galaxy growth. Some jets point almost directly at Earth, creating especially bright and variable objects called blazars. The orientation matters tremendously for what we observe. A galaxy with jets pointed sideways looks different from one with a jet pointed at us. These relativistic jets are one way that supermassive black holes influence their cosmic surroundings on scales far larger than the black holes themselves. And jets are characteristic of a particular class of active galaxies. Radio galaxies emit powerful radio waves from their central black holes. These galaxies were among the first AGN discovered, detected through radio telescope surveys that revealed sources far brighter in radio emission than could be explained by normal star formation. The radio emission comes from the jets and lobes. Relativistic electrons spiraling in magnetic fields produce synchrotron radiation, brightest at radio wavelengths. A classic radio galaxy appears in images as a bright central source, the galaxy and its AGN, flanked by two enormous radio lobes extending far beyond the visible galaxy, filled with plasma ejected by the jets perhaps millions of years ago. These lobes can be millions of light years across, dwarfing the galaxy itself. Radio galaxies are typically giant ellipticals, often found at the centers of galaxy clusters. The supermassive black holes powering them can be billions of times the Sun's mass. Observing radio galaxies at different wavelengths reveals different aspects. Optical images show the stellar population. X-ray images reveal hot gas. Radio images trace the extent of jets and lobes. Together, these observations paint a picture of black holes as not just consumers but also producers, ejecting energy and material that shape their galactic environments over vast distances and timescales. And different types of AGN have their own characteristics. Seyfert galaxies have active nuclei but are less luminous than quasars. Named after Carl Seyfert, who catalogued them in 1943, Seyfert galaxies are spirals with unusually bright centers. Their nuclei show strong emission lines in their spectra, indicating hot, energetic gas. They're powered by the same physics as quasars, accreting supermassive black holes, but at lower luminosity levels. The difference between Seyferts and quasars is essentially one of degree. Quasars are more luminous, their AGN output often overwhelming the light from surrounding stars, while in Seyferts, the galaxy itself remains visible. Seyferts come in two types. Type 1. Seyferts show both broad and narrow emission lines in their spectra, suggesting we're viewing the accretion disk relatively directly. Type 2 Seyferts show only narrow emission lines, suggesting our view of the inner accretion disk is blocked by a torus of dust and gas. This classification scheme, based on viewing angle rather than intrinsic differences, was revolutionary in understanding AGN. It suggested that many different types of AGN might be the same objects viewed from different perspectives. Seyfert galaxies are relatively common in the nearby universe, allowing detailed study of AGN physics in less extreme systems. And the most extreme orientation effects occur in objects called blazars. Blazars are active galaxies with jets pointed directly at Earth. When we happen to look down the barrel of a relativistic jet, we see a blazar, an object that appears exceptionally bright and variable. The jet's emission is beamed toward us by relativistic effects, making it appear much brighter than if viewed from the side. Blazars can vary dramatically in brightness over days or even hours, as instabilities in the jet create blobs of material that move outward, producing flares when they interact with surrounding magnetic fields. These objects are among the most energetic and variable in the sky, emitting strongly across all wavelengths from radio to gamma rays. They're relatively rare because the jet orientation must be nearly perfect within a few degrees of our line of sight. But when we find them, they're spectacular. Blazars help us understand jet physics by allowing us to observe jet emission most directly. They're also useful as probes of the intergalactic medium. Their light passes through intervening gas and dust on its way to us, and careful analysis can reveal properties of this intervening material. And all these diverse types of active galaxies share a common energy source. The energy from active galaxies comes from matter falling into the supermassive black hole. Gravity is incredibly efficient at extracting energy from infalling matter. As material spirals inward toward a black hole, gravitational potential energy converts to kinetic energy and heat. The accretion disk becomes extraordinarily hot, radiating intensely. Near the event horizon, conditions become so extreme that a significant fraction of the infalling matter's rest mass energy, the E equals mc squared energy, can be converted to radiation. This makes black hole accretion one of the most efficient energy production mechanisms known, far more efficient than nuclear fusion. A black hole converting 10% of infalling matter's mass to energy is not unusual, whereas fusion converts less than 1%. This efficiency explains how relatively small regions, the accretion disk might be only a few light days across, can produce luminosities exceeding that of entire galaxies containing hundreds of billions of stars. A supermassive black hole accreting at high rates can regulate the evolution of its host galaxy, its energy output affecting star formation across thousands of light years. Understanding AGN means understanding how matter behaves in the most extreme gravitational fields, and how that behavior couples to galaxy-scale processes. And this activity can have profound effects on the larger galactic structure. Active galaxies can affect star formation across their entire structure. The energy output from an AGN doesn't just escape into space, it interacts with gas throughout the galaxy. Radiation can heat gas, increasing its pressure and preventing gravitational collapse. Jets plow through the interstellar medium, creating shockwaves that heat and disperse gas. Winds driven by radiation pressure or by supernovae in the starburst regions surrounding the AGN can blow gas out of the galaxy entirely. This feedback can be negative, suppressing star formation, or positive, compressing gas and triggering new star formation. The balance between these effects shapes galactic evolution. In massive elliptical galaxies, AGN feedback is thought to be responsible for keeping them red and dead, preventing gas from cooling and forming stars, maintaining their quiescent state. Without AGN feedback, simulations predict these galaxies would convert too much gas into stars, producing galaxies bluer and more massive than we observe. AGN feedback is thus a crucial ingredient in galaxy evolution models, a mechanism by which tiny central black holes regulate the growth of structures 1,000,000 times larger. It's a remarkable example of how processes on vastly different scales connect in the cosmic ecology. And galaxies don't exist as isolated objects but gather into larger structures. Galaxies often gather in groups and clusters held together by gravity. Just as stars cluster into galaxies, galaxies cluster into groups and clusters. A galaxy group is a small collection, perhaps a few dozen galaxies bound by mutual gravitation, like our local group. A galaxy cluster is larger, containing hundreds to thousands of galaxies orbiting within a region perhaps 10 million light-years across. These structures are gravitationally bound. The galaxies orbit their common center of mass, held together by gravity, not being carried apart by cosmic expansion. Within clusters, galaxies move at high speeds, hundreds or thousands of kilometers per second, their velocities balanced by the cluster's gravitational pull. Clusters are dense environments where interactions are common. Galaxies can pass close to each other, their gravitational tugs stripping gas and stars. They can collide and merge. The space between cluster galaxies isn't empty, but filled with hot gas, the intracluster medium, heated to tens of millions of degrees by the cluster's gravitational potential. This hot gas glows in X-rays, sometimes outmassing all the galaxy's stars combined. Clusters are cosmic laboratories where environmental effects shape galaxy evolution, and they're also among the universe's most massive structures. Galaxy clusters can contain hundreds or thousands of galaxies. The richest clusters are impressive structures. The Coma cluster, for instance, contains over 1,000 large galaxies and countless smaller ones, all orbiting within a region about 20 million light-years across. The total mass is enormous, perhaps 1,000 trillion times the Sun's mass, with most of that mass in dark matter, some in hot intracluster gas, and perhaps 5% in stars. At the cluster's center typically sits a massive elliptical galaxy, sometimes called a CD galaxy, which has grown fat by cannibalizing galaxies that ventured too close. Around it swarm hundreds of other galaxies, mostly ellipticals and lenticulars in rich clusters, their gas stripped away by interactions. The dense environment of a cluster affects galaxy evolution profoundly. Spiral galaxies falling into clusters can be transformed into lenticulars as their gas is stripped away by ram pressure, the force of moving through the intracluster medium, like a wind stripping leaves from a tree. High-speed encounters between galaxies can trigger starbursts or harassment effects that disrupt structure. Clusters are dynamic ecosystems where galaxies evolve differently than they would in isolation, shaped by their dense environments, and the nearest such massive cluster is relatively close by. The Virgo cluster is the nearest large galaxy cluster to us, located about 54 million light-years away in the constellation Virgo. This cluster contains over 1,300 galaxies and has been intensively studied as our closest example of a rich cluster. The Virgo cluster's gravitational pull affects the local group. We're being drawn toward it, though the motion is subtle compared to the overall expansion of the universe. At Virgo's heart sits M87, a giant elliptical galaxy famous for being the first galaxy where a supermassive black hole's shadow was directly imaged by the Event Horizon Telescope. The cluster contains a mix of galaxy types, though ellipticals and lenticulars dominate as expected in cluster environments. Observations of the Virgo cluster have been crucial for establishing the cosmic distance scale. By measuring distances to Virgo galaxies using various methods, astronomers calibrate the relationships used to estimate distances to more remote clusters. The Virgo cluster is close enough that we can study individual galaxies in detail, yet far enough to observe the cluster as a coherent structure. It's a key nearby laboratory for understanding how galaxies behave in dense environments, and for studying cluster-scale phenomena like the hot intracluster medium and the effects of environment on galaxy evolution. The Coma cluster contains over 1,000 identified galaxies. Further away than Virgo, at about 330 million light-years distance, the Coma cluster is one of the richest clusters known. It's dominated by elliptical and lenticular galaxies. Over 85% of bright cluster members fall into these categories, typical of very rich clusters where environmental effects have been strongest. The Coma cluster was historically important in astronomy. In the 1930s, Fritz Zwicky studied the motions of galaxies in Coma and realized that their velocities were too high. The cluster's visible matter couldn't provide enough gravity to hold it together. Galaxies should be flying apart, yet the cluster was stable. Zwicky proposed that unseen matter, he called it dark matter, must be present to provide the additional gravitational binding. His calculation was remarkably accurate. Modern estimates suggest dark matter comprises about 85% of the Coma cluster's total mass. The cluster's center contains two giant ellipticals, NGC 4874 and NGC 4889, each having grown through countless mergers. The hot intracluster medium in Coma is well studied, glowing brightly in X-rays. Coma remains an important target for studies of cluster dynamics, dark matter distribution, and environmental effects on galaxies. Hot gas between galaxies in clusters emits X-rays. The space between cluster galaxies isn't empty, but filled with diffuse gas heated to temperatures of tens of millions of degrees Kelvin. This intracluster medium is hot enough that atoms are fully ionized, electrons stripped from nuclei, and the free electrons emit X-rays through various processes. This hot gas often outweighs all the stars in all the cluster's galaxies, making it the dominant form of normal matter in the cluster. Though still far less massive than the dark matter, the gas got hot through multiple processes. As the cluster formed, gravitational potential energy converted to heat as gas fell into the deepening gravitational well. Galaxy motions create shock waves that heat gas. A GN activity injects energy. The result is a vast hot atmosphere permeating the cluster. X-ray observations of this gas are crucial for understanding cluster physics. The gas distribution traces the cluster's gravitational potential, providing maps of where dark matter is concentrated. The gas temperature and density tell us about the cluster's mass and formation history, and the chemical composition reveals metals produced by supernova in cluster galaxies, mixed into the intracluster medium over billions of years. The hot intracluster medium is a record of cluster evolution written in diffuse plasma. Galaxy clusters are the largest gravitationally bound structures in the universe. Larger structures exist, superclusters, filaments of the cosmic web, but these aren't gravitationally bound. They're being pulled apart by cosmic expansion, their components moving away from each other, just more slowly than more distant structures. Galaxy clusters, however, are bound. They've collapsed under their own gravity, separated from the general expansion, their member galaxies orbiting within the cluster's gravitational potential. A rich cluster might contain a quadrillion solar masses of matter, mostly dark matter, but with substantial amounts of hot gas and stars, all held together by gravity within a region 10 to 20 million light-years across. These are the largest relaxed systems in the universe, structures that have had time to settle into equilibrium, their components' random motions balanced by gravitational attraction. Studying clusters tells us about the universe's structure and evolution on the largest scales. Cluster abundance, how many clusters of various masses exist, constrains cosmological parameters, telling us about dark matter, dark energy, and the universe's overall geometry. Clusters are laboratories for extreme physics, containing the hottest gas, strongest gravitational lenses, most massive galaxies. They're cosmic crossroads where environmental effects most strongly shape galaxy evolution. Superclusters are groups of galaxy clusters, though not gravitationally bound. On even larger scales than clusters, we find superclusters, regions where multiple galaxy clusters and groups congregate, connected by filaments of galaxies, separated by voids. But unlike clusters, superclusters aren't bound structures. Cosmic expansion wins at these scales. The components of a supercluster are moving apart from each other, carried by the expansion of space, though more slowly than the cosmic average because of their mutual gravitational attraction. Superclusters can span hundreds of millions of light-years, containing dozens of galaxy clusters and thousands of individual galaxies. They trace out the largest elements of the cosmic web, the filamentary structure visible in galaxy surveys. The Milky Way belongs to a supercluster, and naming it required recognizing the pattern of galaxies around us. For a long time, it was thought we belonged to the Virgo supercluster, centered on the Virgo cluster. More recent studies revealed a larger structure, and our actual supercluster has a different name. The Milky Way is part of the Laniakea supercluster. Laniakea, a Hawaiian name meaning immense heaven, is the supercluster containing the Milky Way and about 100,000 other galaxies. Defined in 2014 by mapping the velocities of galaxies in our cosmic neighborhood, Laniakea represents a basin of attraction, a region where galaxies' motions are influenced by a common gravitational pull. The supercluster is about 520 million light-years across, containing the Virgo cluster, and therefore our local group, as just one component among many. At Laniakea's heart lies the Great Attractor, a region of overdensity that draws galaxies toward it. Identifying Laniakea required careful analysis of galaxy motions, separating the component due to cosmic expansion from the component due to local gravitational attraction. The result is a map of our cosmic neighborhood, showing how we're connected to surrounding structures through the web of gravity. Laniakea isn't isolated, it's adjacent to other superclusters, and together they form even larger structures in the cosmic web. But at these enormous scales, structures become increasingly diffuse, increasingly dominated by expansion rather than gravitational binding. Laniakea represents perhaps the largest structure we can meaningfully call our home. Laniakea contains about 100,000 galaxies. This is an enormous number, yet it represents only a tiny fraction of all galaxies in the observable universe. Those 100,000 galaxies contain quadrillions of stars, so many that if you could count one per second, you'd need trillions of years to count them all. And each of those stars might have planets, moons, asteroids, comets. The total number of worlds within Laniakea is beyond comprehension. Yet, for all this abundance, Laniakea occupies only a small volume of space. The observable universe contains perhaps hundreds of similar superclusters, each with its own population of galaxies. When we contemplate these scales, 100,000 galaxies in our supercluster, billions of galaxies in the observable universe, we confront the universe's true immensity, and we realize that everything familiar to us, every human experience, every historical event, happens on one planet orbiting one star in one galaxy among 100,000 in just one supercluster among hundreds. The scales humble us, yet also inspire wonder. We're tiny, but we're capable of measuring and understanding these vast structures, of placing ourselves within the cosmic architecture, of knowing our address in the universe. And galaxy clusters have one more remarkable property that makes them useful as cosmic telescopes. Galaxy clusters act as gravitational lenses, bending light from more distant objects. Einstein's general relativity predicts that mass curves spacetime, and light follows those curves. A massive object like a galaxy cluster creates a significant gravitational well, and light from distant galaxies behind the cluster passes through this curved spacetime, its path bent. From our perspective, this creates lensing effects. Background galaxies appear distorted, stretched into arcs or multiple images. Sometimes the cluster's gravitational field can magnify distant galaxies, making them appear brighter and larger than they would without lensing. Astronomers use cluster lensing in two ways. First, By measuring how much background galaxies are distorted, they can map the cluster's total mass distribution, including dark matter. Gravitational lensing is sensitive to all mass, not just luminous matter. Second, they use clusters as natural telescopes, exploiting the magnification to study distant galaxies that would otherwise be too faint to observe in detail. Some of the most distant galaxies known were discovered this way, magnified by foreground clusters. Gravitational lensing turns clusters into cosmic laboratories for both dark matter physics and early galaxy formation. It's a beautiful confirmation of general relativity and a practical tool for observing the distant universe. Dark matter makes up roughly 90 to 95% of an individual galaxy's total mass, while visible stars and gas form only a small fraction. When we measure a galaxy's total mass by observing rotation speeds, by watching satellite galaxies orbit, by measuring gravitational lensing, we find far more mass than we can see. The visible stars, gas, and dust account for perhaps 5 to 10% of the total. The rest is dark matter, detectable only through its gravitational effects. This ratio means that what we see when we observe a galaxy is just a small tracer of a much larger, invisible structure. The dark matter halo extends far beyond the visible disk, creating a vast spherical envelope within which the luminous matter sits. This dark matter is essential. Without it, galaxies couldn't have formed, couldn't hold themselves together, would fly apart due to their rotation. Yet despite its importance, we still don't know what dark matter is made of. It's not ordinary matter. It doesn't interact with light, doesn't form atoms as we know them. Leading candidates include exotic subatomic particles that interact only through gravity and the weak nuclear force, but decades of searches have yet to detect such particles directly. Dark matter remains one of astronomy's greatest mysteries, a reminder that the universe we see is only a fraction of what exists. We detect dark matter only through its gravitational effects. Dark matter doesn't emit, absorb, or reflect light at any wavelength. It doesn't interact electromagnetically. We can't see it, photograph it, or detect it with any telescope that observes electromagnetic radiation. Yet we know it's there because of how it affects things we can see. Galaxies rotate faster than they should based on visible matter alone. Dark matter provides the extra gravity. Galaxy clusters have more gravitational lensing than their visible mass can produce. Dark matter bends the light. The universe's large-scale structure matches predictions only if dark matter is included in simulations. Its gravity shaped the cosmic web. The cosmic microwave background's temperature fluctuations reflect the influence of dark matter in the early universe. Every observation that depends on gravity reveals dark matter's presence. It's like watching leaves swirl in a wind we cannot feel, or seeing ripples on water caused by something invisible beneath the surface. We know the effect, we can measure it precisely, but the cause remains mysterious. Numerous experiments seek to detect dark matter particles directly, to capture the rare interaction when a dark matter particle strikes ordinary matter. So far, these searches have come up empty, but they continue, refining techniques, pushing to greater sensitivity. And while dark matter remains mysterious, some galaxies present even stranger puzzles. Some galaxies appear to have very little dark matter, defying our understanding. In recent years, astronomers have discovered galaxies that seem to contain much less dark matter than expected, or possibly none at all. These ultra-diffuse galaxies, particularly ones like NGC 1052-DF2 and DF4, challenge our models. If galaxies form within dark matter halos, How can some galaxies have little or no dark matter? Several explanations have been proposed. Perhaps these galaxies formed normally, but had their dark matter stripped away through interactions with other galaxies, tidal forces pulling away the dark matter halo while leaving stars behind. Perhaps they formed in unusual environments where dark matter was scarce. Or perhaps there are formation mechanisms we don't yet understand. Alternatively, some argue that these galaxies might not be as dark matter-free as initially thought. Distance uncertainties or measurement errors could explain the apparent deficit. The debate continues, with new observations and refined measurements. These anomalous galaxies are important because they test our theories. If dark matter is fundamental to galaxy formation, finding galaxies without it is surprising and demands explanation. Conversely, if dark matter theories are wrong and gravity behaves differently than we think, these galaxies might be key evidence. Either way, they're puzzles that drive science forward, anomalies that force us to question our assumptions. Rogue stars drift through intergalactic space, ejected from their home galaxies. Not every star remains bound to the galaxy where it formed. During galaxy mergers, gravitational interactions can fling stars out at high velocities, sending them on trajectories that carry them away from any galaxy into the vast darkness of intergalactic space. Simulations suggest that as much as 10 to 50% of all stars in galaxy clusters might be intergalactic, drifting between galaxies rather than bound within them. These rogue stars are difficult to detect. They're spread so thinly that imaging them individually is nearly impossible except in nearby clusters. But astronomers have detected their faint, diffuse glow, an intra-cluster light that pervades the space between cluster galaxies. This light comes from billions of orphaned stars ejected during past mergers, now wandering through intergalactic space. If you stood on a planet orbiting an intergalactic star, the night sky would be profoundly dark. No Milky Way arcing overhead. No nearby galaxies bright enough to see without a telescope. Just a few distant smudges and the faint glow of cluster galaxies millions of light years away. It would be an isolated, lonely existence in the cosmic voids between islands of light. Ultra-compact dwarf galaxies might be the stripped cores of larger galaxies. These strange objects are dense, small, only a few hundred light years across, but containing millions of stars. They're more massive than globular clusters, but smaller than typical dwarf galaxies, and their origins have puzzled astronomers. One leading theory suggests they're the remnants of larger dwarf galaxies that fell into galaxy clusters. Tidal forces stripped away the outer stars, gas, and dark matter, leaving behind only the dense central core. These cores, being most tightly bound, survived the stripping process. Evidence supports this scenario. Some ultra-compact dwarfs show signs of stripped material streaming away, chemical compositions suggesting complex star formation histories, and central supermassive black holes more massive than expected for their current size, black holes that match what we'd expect for the original larger galaxy. If this theory is correct, ultra-compact dwarfs are galactic skeletons, the dense hearts of once larger systems exposed by tidal stripping. They're cautionary tales of what happens when small galaxies venture into dangerous environments, coming too close to larger galaxies or falling into dense clusters where tidal forces reign supreme. And galaxies large and small can have their own families of companions. Satellite galaxies orbit larger galaxies like moons around a planet. Just as planets have moons, galaxies have satellites, smaller galaxies held in orbit by gravitational attraction. The Milky Way has dozens of known satellites, ranging from the relatively large Magellanic Clouds to tiny dwarf spheroidals containing only a few thousand stars. These satellites orbit on timescales of hundreds of millions to billions of years, some on nearly circular paths, others on highly elliptical trajectories that carry them far from their parent galaxy before plunging back inward. The relationship between galaxies and their satellites is complex. Satellites are slowly being destroyed by tidal forces, their material gradually absorbed into the larger galaxy. Yet new satellites can be captured if conditions are right. The satellite population thus changes over time, a dynamic system responding to gravitational interactions and the ongoing accretion of material from the cosmic web. Studying satellite galaxies helps us understand dark matter. Satellites' orbits trace the dark matter halo's gravitational potential. They also help us understand galaxy formation. Many satellites contain ancient stellar populations, preserving clues about early cosmic history. And they remind us that galaxies don't exist in isolation but in families, bound together by gravity into hierarchical systems. The Milky Way has dozens of known satellite galaxies. Current catalogues list about 60 satellite galaxies orbiting the Milky Way, though the exact number depends on where you draw the boundaries and how faint an object you count as a galaxy. The largest and brightest are the Magellanic Clouds, visible to the naked eye from the southern hemisphere. Most others are faint dwarf spheroidal galaxies, discovered through careful surveys searching for overdensities of stars. Some are so faint, so diffuse, they contain only a few thousand stars and were discovered only in the 21st century using data from modern wide-field surveys. Each new satellite discovery adds to our understanding of the Milky Way's gravitational influence and mass. But theory predicts we should see more satellites than we do. This is called the missing satellites problem. Simulations of dark matter predict hundreds or thousands of dark matter subhalos orbiting the Milky Way, yet we see only dozens of satellite galaxies. Perhaps most dark matter subhalos fail to form stars, remaining dark. Perhaps our simulations overpredict subhalo numbers. Or perhaps many satellites are yet undiscovered, too faint for current surveys. As surveys become more sensitive, we continue finding new satellites, gradually closing the gap between prediction and observation, but the discrepancy remains an active area of research. There may be billions of galaxies in the observable universe. Early estimates based on Hubble Deep Field images suggested perhaps 100 to 200 billion galaxies. More recent analyses, accounting for small, faint galaxies that deep surveys might miss, push that number higher, perhaps 1 to 2 trillion galaxies in the observable universe. The uncertainty is large because counting faint, distant galaxies is difficult. We can count bright ones relatively easily, but how many faint dwarfs exist? How many ultra-diffuse galaxies are we missing? The answer depends on the galaxy luminosity function, how many galaxies exist at each brightness level, and on our ability to detect the faintest ones. But whether the number is hundreds of billions or a few trillion, the point remains. Galaxies are extraordinarily abundant. The observable universe is filled with them, scattered through space in every direction we look. Each one is a vast structure in its own right, containing millions to trillions of stars. The total number of stars in the observable universe, if there are 1 trillion galaxies averaging 100 billion stars each, might be 100 billion trillion, a number so large it loses meaning. Yet each one is an individual sun, obeying the same physics that governs our own, and each galaxy carries within it a unique story. Every galaxy we see tells a story billions of years in the making. A galaxy's current appearance, its size, shape, color, star formation rate, reflects its entire history. The stars we observe now formed at different times, some billions of years ago, some recently. Their chemical compositions record the history of element production through successive stellar generations. The galaxy's structure, whether spiral or elliptical, whether compact or diffuse, reflects its formation mechanisms and merger history. The amount of gas present tells us whether star formation continues or has ceased. The central black hole's mass reflects billions of years of growth. When we observe a galaxy, even in a single snapshot, we're seeing the cumulative result of its evolutionary path, the sum of all the processes that have shaped it since the early universe. By studying many galaxies at different distances, different ages, we can reconstruct the story of how galaxies in general evolve, how they change from the small chaotic systems of the early universe to the structured, mature galaxies we see nearby. Each galaxy is a unique outcome of physical processes playing out over cosmic time, and together they tell the story of structure formation in the universe, of how gravity and gas dynamics and dark matter and stellar evolution conspired to create the diverse galactic zoo we observe. New galaxies are still being discovered with every advancement in telescope technology. Despite centuries of astronomical observation, we haven't finished cataloguing the universe's galaxies. Each improvement in telescopes, larger mirrors, better detectors, longer exposure times, new wavelengths, reveals previously unseen galaxies. Ultra-faint dwarf galaxies around the Milky Way continue to be discovered as surveys become more sensitive. Distant galaxies at high redshift appear in new deep fields. Ultra-diffuse galaxies, so faint they're nearly invisible, are being identified in cluster surveys. Gravitational lensing magnifies distant galaxies that would otherwise be undetectable. Each discovery adds to our census, refines our understanding of galaxy populations, sometimes challenges our theories. The James Webb Space Telescope, with its infrared sensitivity, is discovering galaxies at redshifts where previous telescopes saw nothing. Future telescopes, the Nancy Grace Roman Space Telescope, extremely large ground-based telescopes, will push further, finding fainter, more distant, more unusual galaxies. The process of discovery continues, and will continue for decades, each new galaxy adding a piece to the puzzle of cosmic structure and evolution. We're still exploring the universe, still finding surprises, still learning what kinds of galaxies exist and where they're hiding. The diversity of galaxies reflects the complexity of physical processes shaping them. No two galaxies are exactly alike. Each has its own mass, its own rotation rate, its own star formation history, its own merger history, its own environment. This diversity emerges from the interplay of gravity, gas dynamics, star formation, stellar feedback, dark matter, cosmic expansion, and countless other factors. A galaxy forming in a dense environment experiences different influences than one forming in isolation. A galaxy that experienced an early major merger evolves differently than one that grew through gradual accretion. The initial density fluctuations in the early universe, the timing of gas infall, the presence or absence of nearby galaxies, all these factors and more shape each galaxy's unique trajectory through time. The result is a universe filled with variation, where spirals and ellipticals and irregulars coexist, where massive galaxies and dwarfs populate the same regions, where active galaxies and quiescent ones sit side by side. This diversity is beautiful in itself, a demonstration of how simple physical laws can generate complex, varied outcomes, and it's scientifically valuable. By comparing galaxies with different properties, we can isolate the effects of specific processes, testing our theories against the full richness of nature. Galaxies remind us of our place in a vast, ancient and beautiful universe. When we look at galaxies, whether through telescopes or in photographs, whether as mathematical models or as pale smudges in the night sky, we're reminded that we live in a cosmos of staggering scale and age. The Milky Way is 13.6 billion years old, nearly as ancient as the universe itself. It contains hundreds of billions of stars, each one a sun, many with their own planets. And the Milky Way is just one galaxy among billions or trillions scattered through space, each separated from the next by millions of light years of mostly empty space. We occupy one planet orbiting one star in one galaxy, a tiny mote in this vast cosmic ocean. Yet from this small vantage point, we've learned to measure the universe, to trace its history, to understand the physical laws that govern its evolution. We've learned that we're made of elements forged in ancient stars, that our atoms once drifted through interstellar space before gathering into the Sun and Earth. We're connected to the cosmos through physics and chemistry, through the shared history of matter and energy. And we're connected through observation and understanding, through our ability to look outward, to wonder, to learn. Galaxies are not just objects of scientific study, but sources of wonder, invitations to contemplation, reminders of both our smallness and our capacity for understanding. They've been turning slowly through the void for billions of years, and they'll continue turning long after humanity is gone. Islands of light in the cosmic dark. Let these thoughts settle gently now. Let the scale of galactic space, galactic time, enfold you like a soft blanket. You are small, yes, but you are also part of this universe, made of the same matter, governed by the same laws, connected through the long chain of cosmic history. The galaxies continue their slow rotation through the void. Stars are born and die. Light travels across millions and billions of years, and somewhere on a small blue planet orbiting an ordinary star in an ordinary galaxy, you rest now, held by gravity, breathing ancient atoms, contemplating the cosmos. Sleep well among the galaxies. Let the darkness be gentle, the vastness soothing. Tomorrow the stars will still be there, turning slowly, patiently through the infinite night. Good night.